Hello and welcome to Sleepy Science. Tonight, let's dim the lights and drift to the quiet edge of knowing, where the universe folds into questions that hum beneath certainty. We'll trace invisible threads that hold galaxies together, listen for echoes that travel faster than time's patience, and watch horizons not as endings but as soft frontiers of curiosity. Together, we'll follow space where it curves, stars that vanish into their own gravity, and light that forgets where it began. Every idea tonight will stretch the way you think. Distance, time, and truth are measured slowly, gently, until the cosmos feels close enough to breathe. And before we fade into that stillness, tell me in the comments where you're watching from. And if these calm journeys help you see differently, tap the like button, subscribe, and keep exploring with Sleepy Science, where wonder never rushes. Dark matter, the invisible mass holding galaxies. Together, you notice it first in a spin that refuses to slow, at the outskirts of a spiral galaxy. Stars whip around almost as quickly as those near the core. A behavior that shouldn't happen if only the matter you can see, stars, gas, dust, were providing the gravity. Something unseen is contributing most of the pull. And we call that something dark matter, not because it's sinister, but because it does not glow, reflect, or absorb light in ways we can easily measure. And yet its gravity leaves tracks everywhere you look when you know how to look. Start with a clue that changed the conversation in the 1970s. Vera Rubin and Kent Ford measured rotation curves of galaxies and found them strangely flat rather than falling off with distance. Decades earlier, Fritz Zwicky had hinted at the same kind of mismatch in galaxy clusters, coining missing mass. And together these lines of evidence told a simple story. Either gravity behaves differently on large scales, or there is far more mass than the luminous sensor suggests. The sky then offered new tests. When a massive cluster sits between you and a more distant galaxy, its gravity can bend the background light and stretch it into arcs and rings, a phenomenon called gravitational lensing that acts like a cosmic X-ray for the invisible. The amount of bending often requires several times more mass than the stars and hot gas can supply. A quiet but stubborn hint that the dominant scaffolding is hidden. If you want a striking example, consider the bullet cluster, where two clusters collided and their hot gas visible in X-Ross lagged behind, while the main mass, revealed by lensing, sailed ahead with the galaxies. In other words, the heavy stuff seemed to pass through itself with little friction, just as you'd expect from matter that interacts mostly through gravity and not much else. On even larger scales, the afterglow of the Big Bang cosmic microwave background has tiny temperature ripples, whose pattern encodes the cosmic inventory. And those ripples say that ordinary atoms are only a small fraction of the universe's content, while a larger share is this dark matter whose presence guided the growth of the cosmic web, helping small seeds of density become galaxies and clusters without smearing away in the early heat. You are living inside one of its structures now. The Milky Way sits in a vast, roughly spherical halo of dark matter that extends far beyond the luminous disk, holding satellite galaxies in their paths and shaping the way our own stars move. You cannot hold this halo in your hand, but its gravity holds you in your orbit around the center, and that's a kind of touch. Because we don't see it, we ask what it could be. And the menu spans from once fashionable ideas-dim stars, cold clouds, black holes too faint to notice in bulk to more likely non-atomic particles that ignore light yet respond to gravity. Compact objects have been searched for through microlensing and other methods and can't make up enough of the missing mass. So attention has turned to new particles such as WIMPs, ixions, sterile neutrinos, or ultralight fuzzy candidates whose wave-like behavior would subtly change how small galaxies form. To meet such elusive visitors, physicists build quiet rooms deep underground and fill them with extraordinarily pure materials like liquid xenon, waiting for an almost impossibly gentle nudge that would betray a dark particle bouncing off an atomic nucleus. These experiments, Sluck-Zeppelin, Xenont, Pandex, and others, have not yet heard the unmistakable knock, which is itself a result, narrowing where dark matter can hide. Astronomers listen from above as well. Telescopes search for secondary clues such as faint gamma rays, neutrinos, or positrons that might arise if dark particles occasionally annihilate or decay. But each claimed whisper must survive the chorus of ordinary astrophysical sources that can sing the same notes. Colliders join the hunt from a different angle, smashing particles together at high energies and looking for missing momentum that hints at something invisible slipping away. So far, the emptiness in those plots is another boundary that guides thinking rather than a defeat. It is fair to ask whether gravity itself needs rewriting instead of inventing a new kind of matter. Modified gravity ideas can mimic certain galaxy rotation curves with fewer moving parts, and that proposal deserves respect. Yet when you check the full ledger cluster lensing, the bullet clusters, masca separation, the detailed pattern of the microwave background, and the way structure emerged over time, ordinary gravity plus dark matter still ties more facts together with one consistent rope than the alternatives currently do. Of course, consistency is not certainty, and the history of science rewards the humility to keep testing favorite ideas until they either break or endure. That is why the next generation of sky surveys and space missions will map subtle distortions of background galaxies' weak lensing, cosmic shear across huge patches of sky, draw exquisite 3D maps of galaxy clustering, and trace the motions of stars in unprecedented detail, all to ask the same patient question: where exactly is the mass, and how does it flow? As these maps sharpen, they will probe whether dark matter is perfectly cold and collisionless, or has a small self-interaction that rounds galaxy cores or changes the dance of satellites, whether ultralight versions create delicate interference patterns in dwarf galaxies, whether ixions leave a radio signature in magnetic fields, or whether a clever laboratory resonator can coax them to reveal a faint, periodic whisper. Through all of this, the most honest sentence remains surprisingly comforting. We don't yet know what dark matter is, but we know many things it is not, and we know how it behaves gravitationally well enough to use it as a working tool to explain motions, bendings, and growth. The mystery is not a hole in knowledge, but a frontier with coordinates. And if you are wondering what to do with a truth you cannot touch, consider what it suggests about your ordinary life. Causes need not be visible to be real. Most of what shapes a system can be in its background. And sometimes you learn more by measuring the responsa curve that refuses to fall, a light that arcs where space is heavy, than by staring at the brightest objects. That is not mysticism, just method. So let the introduction settle. There is extra gravity in the room. Let the development do its work. We found it by weighing motion, by watching light bend, by reading the Big Bang's Afterglow, by following how structure formed, and by trying tirelessly to catch a particle in the act. And for a soft close, breathe out with this: the night sky is not withholding answers so much as offering a pace-low, careful, cumulative where certainty grows, one constraint at a time. When you fall asleep under that sky, Remember, you are resting inside a halo that has held your galaxy together for billions of years. An invisible kindness that asks for no credit and offers you a wider sense of home. Dark energy, the unknown force, speeding up expansion. You expect the universe to behave like a tossed stone, fast at first, then slowing under gravity's steady tug-but. The surprising truth is that the cosmic stone is speeding up, and the name we give that runaway behavior is dark energy. A placeholder for a real effect first revealed in the late 1990s, when two independent teams used exploding stars, type Ia supernovae as mileposts, and found that faraway ones were dimmer than a slowing universe would allow, as if the space between us had stretched more than expected while their light was en route. That discovery didn't rest on a single clever trick. It grew from a careful ladder of distances where closer rungs calibrate the farther rungs, letting astronomers compare how bright it should be to how bright it is across billions of years of look-back time. And the pattern in those comparisons told a consistent story. Gravity alone is not winning the long game. Since then, other lines of evidence have joined in different accents, acoustic patterns, fossilized in the way galaxies cluster, provide a second yardstick, and their measured scale at various epochs fits an expansion. History that transitions from early deceleration to late acceleration. While the growth of cosmic structure has been slightly stunted in recent times compared with a universe that only slows, a signature you can read in how clumps of galaxies mature over billions of years. The most economical explanation is not a new kind of matter, but a property of space itself. Call it vacuum energy. Call it the cosmological constant whose density doesn't thin out as the universe expands. Double the volume, and matter becomes half as dense. But this smooth component keeps the same gentle pressure everywhere. And that pressure is strange in one specific way. It acts like tension, encouraging space to pull itself apart more vigorously over time. You can test that idea without heavy math by asking practical questions. If this smooth component truly keeps the same density, distances at given cosmic ages should follow a precise curve. And that is what supernova and galaxy surveys have been tracing. If it really suppresses growth, then the largest clumps of matter should be just a little less mature today than they would be in a purely slowing universe. And that is what multiple surveys find when they compare the sky at different epochs. Still, honest science allows competition. Some researchers try to replace the smooth component with tweaks to gravity on the largest scales. And the way to tell these ideas apart is to check two clocks simultaneously. One clock measures how fast the universe expands. The other measures how quickly structures form, and only a true energy of space tends to make those two clocks diverge in a particular pattern. The hunt now is about the details. Is the cosmic push perfectly steady, or does it evolve with time? Most current measurements say its behavior is remarkably close to a constant, always-on background. Yet a small deviation would be a revolution. And that's why new missions are mapping millions of galaxies in 3 dimensions to read the expansion history more finely, while others watch for extremely subtle shifts in the color of light from very distant objects over decades. A direct way to see expansion change in real time. Another fresh avenue uses collisions of dense stellar remnants as standard. Sirens, because gravitational waves carry an unambiguous measure of distance that can be compared to redshift from the faint light of the same event, offering a distance redshift check independent of traditional methods and less vulnerable to the usual astrophysical machine. Beneath all of this sits a humbling puzzle you can feel even without equations, quantum theories, predict that empty space should seethe with energy far larger than what the universe actually displays. Yet observations say the cosmic push is real, but tiny, so tiny that if a human were that delicate, you could lift a mountain with a sigh and still call it gentle. The mismatch between what theory naively expects and what the sky shows is among the biggest open questions in modern physics. There's also a timing riddle. Why, out of all possible eras, are we living when the smooth component is just beginning to dominate and drive acceleration, rather than much earlier or much later? It might be a coincidence, it might be a selection effect, or it might be a clue that the smooth component is not perfectly steady but has a subtle rhythm we have yet to hear. What should you carry away that is firm and useful beyond the poetry of names? First, acceleration is not a rumor, is a measured feature of the universe supported by independent methods that weigh distances, trace patterns, and track cosmic growth. Second, dark energy is not a creature hiding in the shadows, but a stand-in label for the push we infer from those measurements, most simply modeled as a property of space that does not dilute, and therefore becomes important only after matter has thinned with expansion. Third, we are not done. Upcoming observatories on the ground and in space are designed to test whether this push is absolutely steady, slightly time-varying, or a sign that gravity itself behaves differently on scales no human will ever physically cross. And each outcome would reshape what we mean by nothing, by distance, by future. If you let that sink in gently, the lesson is both practical and philosophical. Not all forces in your life arrive as a shove. Some are background conditions that change the meaning of effort itself, and noticing them early can save you from pushing the wrong way. So let the introduction taper into understanding. Our cosmos does not merely coast, it accelerates. Let the development deepen multiple, independent yardsticks trace the same arc and point to a smooth, nearly constant push, and let the conclusion settle like night air. There is no need to dress the unknown as certainty to make it powerful, because what we can already show is astonishing enough. The universe is teaching you that even emptiness has a say in how everything moves, and that listening carefully over long times is how you turn a bewildering hint into a trustworthy map. Black holes, places where gravity traps, even light. Imagine a place where the very idea of a way stops working. You point an arrow outward and spacetime quietly turns it back, not by breaking physics, but by following it to a limit called an event horizon, a one-way boundary after which every possible future path bends inward. That is the essence of a black hole, no myth, no movie trick, but a real astrophysical object built when enough mass is squeezed into a small enough region that even light runs out of usable paths to escape. The most common recipe begins with a star far heavier than the sun. After burning its fuel and briefly shining in a last violent breath, its core collapses under its own gravity until the material has no pressure left that can resist the fall, and the surrounding layers crash in. If what remains exceeds certain thresholds, the collapse doesn't stop at a dense remnant, punches through to a black hole. From the outside, you never see the interior complete its fall. Clocks near the forming horizon appear to slow and redden, while from the falling material's own point of view it crosses the boundary in finite time. A reminder that different observers tell different but consistent stories in strong gravity. Once a black hole exists, it is surprisingly simple in personality. In practice, it is defined by mass and spin, which set the size of the horizon and how space-time swirls around it. That simplicity means two very different formation histories can lead to nearly identical end products. Although you cannot look inside, black holes announce themselves by how they dine. Gas spiraling inward forms a hot, bright accretion disk, where friction and magnetic fields turn gravitational energy into light that can outshine the entire galaxy for a while. And in some cases, those same magnetic fields thread the spinning hole and help launch narrow jets that fire material at near light speed for thousands of light years, carving straight, luminous lines through space. We know they're real not because someone believes hard enough, but because the sky keeps providing clean, weight-bearing clues. Around the center of our Milky Way, stars trace fast, tight orbits around an unseen object about 4 million times the sun's mass, completing loops in mere years and whipping around a point too small to be anything but a black hole. And for a giant in another galaxy, a global network of radio telescopes acting as one Earth's, I resolved a dark shadow surrounded by a glowing ring, the footprint of light, bent and captured near the horizon, matching calculations of how a black hole's silhouette should look. When two black holes merge, the fabric of spacetime itself rings like a struck bell, sending out gravitational waves that we can measure on Earth as fleeting, exquisitely small stretches and squeezes. Those signals carry the masses and spins of the partners and the ring-down tones of the remnant, letting us test whether the final object behaves like a clean, simple black hole or something stranger. If you were to fly toward one, the experience would depend on its size. Near a small black hole, tidal forces change so abruptly that a person would feel a dramatic stretch and squeeze spaghettification well before the horizon. Near a supermassive one, the same effects could be gentle at the boundary, and the more striking sensation would be time itself misbehaving, with your clock running slower compared with distant ones and the colors of any outgoing light shifting toward the red until they fade from view. A common worry is the singularity, a point inside the mathematics where density climbs without limit. What this really tells you is that our current theories are incomplete in such extremes, not that nature enjoys infinities, and a deeper framework that blends gravity with quantum rules is expected to explain what replaces that naive point. Everything we can check outside the horizon works beautifully. On the quantum side, something even more startling happens. Black holes are not perfectly black but should glow faintly by a process where the horizon allows quantum fluctuations to separate, with one particle falling in and its partner escaping as heat. For stellar and supermassive holes, this Hawking radiation is so weak that it is undetectable with present instruments and utterly irrelevant to their everyday lives. But the idea forces a hard question: what happens to information about the stuff that fell in if the hole ever evaporates? That information paradox has become a crucible for theory, and modern proposals suggest the lost details are not destroyed but encoded in delicate, long-range correlations that leak out over time or are preserved on subtle structures near the horizon, with names you don't need to memorize to grasp the point. The universe is probably consistent about bookkeeping even when the ledger is written in a script we are still learning to read. There are black holes in at least 3 weight classes, stellar mass ones a few to a few dozen times the sun, supermassive ones millions to billions of suns anchoring galaxy centers, and a middleweight group we're still confirming called intermediate mass black holes, hinted at by unusually heavy mergers and compact star clusters. How the biggest ones grew so quickly in the infant universe is an open riddle, with possibilities ranging from rapid feeding frenzies to early, massive seed collapses. If you like practical tests more than labels, the next decade is built for you. Improved radio arrays aim to sharpen images of black hole shadows and even track how the glowing ring flickers over minutes, while gravitational wave observatories on the ground and in space will catch mergers across a wider range of masses, turning one-off discoveries into population statistics and stress tests of gravity in its strongest regime. What should you keep after the wonder settles? First, a black hole is not a hole in the sense of a tear or an absence. It's a region where gravity curves spacetime so completely that inside means future is inward, a precise condition with measurable consequences. Second, we do not infer them only from theory. We weigh the way nearby stars move, we read the hot light from feeding gas, we listen to spacetime vibrate when they collide, and we have imaged the silhouette that strong gravity carves out of surrounding light. Third, the edges of what we know are not excuses for fantasy, but invitations to finer questions. How does spin feed jets? How early did the first giants grow? Where does nature enforce simplicity, and where does it hide detail? And how do quantum rules safeguard information when horizons are involved? Let the introduction open the door. A place exists where light itself is out of options. Let the development teach clearly formation in collapse, simple exterior character, brilliant feeding, orbital and imaging evidence, and the new language of gravitational waves. And let the conclusion be soft but firm mystery. Here is not a fog, but a map. And when you close your eyes tonight, remember that in a universe of scattered lights, there are also deep wells that shape the dance without needing to be seen. Reminders that sometimes the strongest influences are the ones that teach you how to look rather than where. Supermassive black holes at the centers of galaxies start not with a monster, but with a whisper, at the heart of many great island cities of stars. The traffic is guided by something so concentrated and so patient that an object the size of a solar system can outweigh millions or billions of suns. And yet much of the time it sits in near darkness, a supermassive black hole whose influence shows up less as spectacle and more as order stars circling tightly near the core. Gas warmed or flung outward in disciplined streams, and a quiet correlation between the weight of that central engine and the character of the surrounding galactic bulge that hints at a long partnership between the tiny center and the sprawling city around it. To see that partnership without any equations, follow three kinds of evidence that ordinary telescopes and careful timing can give you. First, the choreography of stars that pass close to our own galaxy center, each one tracing an ellipse you can measure over years, moving so fast and so near to a point-like mass that no cluster of smaller objects could fake it. Second, the way gas in other galaxies acts like a neon sign for the hidden mass, bright megamaser rings spinning with clockwork precision that betray an otherwise invisible, compact gravity well. And third, the direct silhouette that radio telescopes, stitched across Earth, have captured around neighboring giants. A dark footprint surrounded by hot light, where gravity bends and captures photons. Each method different, each pointing to the same conclusion. There really is an engine in the middle, and it is supermassive. When that engine feeds well, it doesn't nibble, it blazes. Gas spiraling inward rubs against itself, heats, and radiates so efficiently that for a brief cosmic season the galaxy's core can outshine all its stars combined. The phase we call a quasar or an active nucleus, where ultraviolet light, X-rays, and sometimes long, ruler-straight radio Jets announce that magnetic fields have tapped the spin of the central object in organized chaos into beams that travel for hundreds of thousands of light years when it starves. The same engine becomes almost shy, like the one in our own Milky Way, flickering with sporadic flares but spending most days in a low appetite state. A reminder that the same central mass can wear very different moods depending on what the galaxy delivers to its doorstep. The interesting twist is that this is not just a one-way relationship where the galaxy feeds the center. The center pushes back, and that feedback can reshape everything from the color of starlight to the fate of galaxy clusters. A windy, radiant nucleus can sweep away or heat the gas that would otherwise cool and form new stars, pausing starbirth and making a once young system red and dead, while in giant clusters the steady drumming of jets from the central galaxy stirs and warms the surrounding reservoir, preventing it from collapsing into a torrent of new stars. That delicate thermostat is why astronomers talk about coevolution, because the mass of the central black hole, the velocity spread of stars in the bulge, and the galaxy's star-forming history are entangled in ways that suggest long negotiation rather than accident. If you ask how such giants came to be so early, because we've already seen quasars when the universe was still very young. The options read like origin stories with different tempos. One path begins with light seeds, the deaths of the first massive stars that left modest black holes to grow by steady feeding and mergers until they reached the million solar mass club. Another path imagines heavy seeds, where metal poor, pristine clouds in the early universe collapsed directly into oversized black holes without forming normal stars first, jump-starting growth in a hurry. And a third path allows for chaotic feasts, short periods of superficient, perhaps messy inflow that let ordinary seeds balloon faster than you'd expect from tidy, averaged growth. Fueling any of these paths is a matter of cosmic plumbing. Gravity funnels gas toward the center when galaxies interact or merge, when bars and spiral arms torque the inner disk, or when cold streams quietly deliver fresh material from larger scales. Near the final parsecs, gas must still shed angular momentum to cross the last mile, a task nature handles through turbulence, magnetic fields, and the push-pull of new stars forming and exploding in the same neighborhood, turning the galactic downtown into a lively, evolving ecosystem rather than a simple drain. While mass sets the scale, spin sets the personality. A rapidly spinning supermassive black hole drags the surrounding spacetime into a slow whirl, bringing the inner edge of its disk closer and changing how much energy the inflowing gas can release. And it seems to help organize the biggest, straightest jets, though the gas supply and the broader magnetic environment matter too, so observers now measure spin indirectly by reading the shapes of ion emission lines from the inner disk, and by watching tiny, time-delayed echoes in X-rays as light bounces off different layers near the center, a kind of heartbeat that maps the innermost regions on minute-to-hour timescales. Every so often, the quiet center becomes a trap for a passing star that strays too near. The star is shredded, and a flare rises and fades over months as its remains spiral inward, a tidal disruption event that offers a rare, backlit look at how material streams form and settle, and a reminder that the core is not only a regulator of galactic weather, but also a place where individual lives can end spectacularly. Other times, the center hosts not one but two supermassive black holes locked in a slow, spiraling dance after a galaxy merger, a process that can carve out depleted stellar cores and, in its final stages, release a long, low chord of gravitational waves that a future space-based observatory is designed to hear, turning what used to be a hypothetical into a mapped census of giant marriages across cosmic time. What you can learn from all this without leaning on symbols is that supermassive black hole is not a synonym for cosmic vacuum cleaner or always-on lighthouse, but the name of a central engine whose behavior depends on supply, environment, and history, an engine that can power a quasar, whisper like ours, or punctuate its quiet with rare, dramatic meals. It is also a civic planner, enforcing limits on a galaxy's future by heating or expelling the raw material of new stars, and a historian, encoding its past in the weight of the bulge that grew around it. The most useful questions we ask next are practical ones. How do the smallest seeds form, and which paths dominate at different eras? When do jets become the main feedback channel compared with winds? How do bars and mergers compare as fuel lines? And can we measure spin and mass not once for a showcase object, but for thousands in a way that ties those numbers to the galaxy's color, dust, and quiet or busy past? Those answers are on the way as radio arrays sharpen moving images of glowing rings, as infrared eyes peer to earlier times to find the first busy cores, and as long-term monitoring turns flicker into diagnostic. If you let the lesson sink in, the structure is simple and gentle. The introduction is that every grand city in the sky likely has a compact, heavy heart. The development is that we have watched stars loop, gas whisper, and rings glow in patterns only such hearts can make, and we have traced how their moods push back on their hosts. The conclusion is that this isn't just spectacle, but governance. The smallest region sets conditions for the largest, and learning to read that conversation teaches you to look for quiet centers in your own puzzles, where a concentrated cause can steer a sprawling outcome without ever raising its voice. Rogue planets, worlds drifting alone between the stars. Picture a planet that never sees sunrise, a world that spins under a sky that is always night, drifting through the thin starlight between constellations with no parent star to circle and nor seasons to mark its years. This is a rogue planet, a free-floating world set loose by the rough politics of young solar systems, or born directly from collapsing gas too small to ignite. And although it hides well, we have learned enough to sketch its life in honest detail. The most common path to exile begins early, when a planetary system is young. Giant planets migrate, smaller worlds jockey for space, and close gravitational scuffles fling the lightweights outward like marbles from a crowded ring. A near miss with a newborn giant can boost a planet to escape speed. A passing star in the same nursery can yank it free. And long after the dust settles, a slow reshaping of Orbisor, even the swelling and mass loss of an aging star, can unhook the remaining outsiders and send them wandering. Another path starts outside the family model, in a cold corner of a star-forming cloud. A knot of gas collapses on its own, but never gets massive or hot enough to spark sustained fusion. What emerges looks like a planet in mass and temperature, but has no star because it never needed one. A reminder that nature cares more about formation rules than labels. Once adrift, a rogue planet doesn't stop being a planet. It keeps its rock and metal core if it had one, its ices if it formed far out, its atmosphere if gravity and chemistry can hold it, and if it was thrown out late enough, might keep a retinue of moons that now circle a darkness instead of a sun, with tides and eclipses that only those moons will ever see. You might ask, if these worlds are unlit, how do we know they exist? The honest answer is that we rarely see them in the usual sense, but catch them in moments when gravity betrays them, especially through brief events where a foreground object passing almost directly in front of a distant star acts like a tiny lens and boosts the star's brightness for hours or days. A very short, solitary brightening can point to a planetary mass body with no sign of a host, and a careful look at the shape and timing of that spike lets astronomers estimate the mass and distance well enough to say, this one is likely alone. In young clusters where recent planets and very low-mass objects are still warm from formation, deep infrared images can sometimes pick out free-floating planets directly, glowing faintly in heat rather than reflected light. Their colors and spectra hint at thick clouds, molecules like water or methane, and temperatures too cool for stars but too warm for most rocks. A thermal afterglow that fades over tens to hundreds of millions of years until only the coldest wavelengths carry the story. Counting them is hard but not impossible. Ground-based microlensing surveys that watch millions of stars for these small, sharp brightenings have begun to place limits on how common they are, suggesting there may be at least as many rogue planets as there are bound giant planets, and perhaps especially in star-forming regions populations of Jupiter mass or sub-Jupiter mass drifters that rival the number of stars. Upcoming wide-field space observatories will sharpen those statistics by catching shorter, cleaner events and measuring tiny parallax effects between Earth and space, turning hunches into a real census. What about life and habitability? The question that wakes up even the sleepiest imagination. The absence of a sun sounds like a death sentence. But physical bookkeeping says not all hope is lost. A massive planet with a deep hydrogen atmosphere can trap internal heat so efficiently that it keeps a surface warm for geologic ages, not from starlight but from the slow leak of leftover formation heat and the steady drip of radioactive decay in its interior. And under that blanket liquid water could exist on the surface. More modest worlds might hide oceans beneath ice, sustained by the same internal warmth that keeps Europa and Enceladus active in our own system. And if a rogue kept a large moon from its previous life, the gentle grind of tides could add another heater to the budget. None of this requires wishing on fantasy's geothermal energy is measurable. Hydrogen is a powerful insulator, and chemistry thrives wherever liquids can persistate. The picture remains sober. Such environments would be rare and fragile compared with sunlit Earths, and the life they could host would likely be slow, blind to day and night, attentive to gradients of heat and chemistry rather than color and shadow. The geology of a rogue planet is its weather. With no star to drive winds in a daily rhythm, the atmosphere responds mostly to interior heat, rotational habits, and occasional external nudges like cosmic rays or dust. If the planet rotates quickly, it can build fierce, banded jets and deep storms placed by the Coriolis effect rather than by sunshine. And if its atmosphere is thick, the night-side cold trap that would freeze gases on a bare rock becomes a gentle temperature slope instead of a cliff. The magnetic field, if present, is a shield that changes the feel of interstellar space. A molten, iron-rich core that turns slowly might generate a protective bubble that diverts charged particles and shapes auroras unlike any seen near Earth, glowing not from a star's wind but from the diffuse environment of the galaxy and the planet's own trapped particles. A silent fireworks show under a perpetual Milky Way over long times. A rogue planet orbits the galactic center like a star does, following an elongated path set by its birth neighborhood and the kicks it received. It will drift through clouds of gas, past other stars at wide distances, and on rare occasions, close enough to feel a tug that changes its speed or even captures it temporarily, raising the tantalizing possibility that some bound planets you see today were once rogues recaptured by a passing sun. Their odd tilts and stretched orbits a fossil memory of years spent alone. The hardest part of studying these worlds is their refusal to stay in one place for us to stare at. Microlensing events don't repeat, and the coldest rogues are nearly invisible except in the deepest infrared. So astronomers build strategies that rely on statistics and patience. Watch enough stars for long enough and short events pile up into a distribution of masses and distances. Image young regions with enough sensitivity and moving object tests to separate faint planets from background galaxies, and use follow-up spectroscopy to learn about their atmospheres even when their light is whispered. If you let this knowledge sit for a moment, the educational shape is clear and calm. The introduction is the hook that a world can wander the galaxy in permanent night and still be a world. The development is the concrete pathway of how it gets there, how we detect it, how many there might be, and what its environment allows. The conclusion is a gentle challenge to your sense of what makes a planet alive. Sunlight is not a requirement for chemistry. Gravity writes destinies that don't need a star. And the cosmos contains more kinds of home than your eyes would guess. If you ever feel lost under a sky that won't lighten, remember the rogue planets that keep moving anyway. Their maps are made of motion, their clocks are written in heat, and their stories prove that being unmoored is not the same as being empty, that even far from a guiding light. There are slow ways to keep warm, slow ways to learn, and slow ways to belong. Fast radio bursts, millisecond signals from deep space. A discovery can arrive like a click you almost miss. A single millisecond in which a radio telescope sees a star-sized shout from a galaxy you'll never visit. A burst so quick and bright that, when you slow it down and spread it by color, the higher pitches reach your receiver first, and the lower ones arrive a breath later, as if the signal had been combed by the thin gas between galaxies. That tiny delay is the fingerprint that tells you what you're hearing is a fast radio burst, a flash of radio light that crosses millions or billions of light years and still slaps your instrument awake. You don't need equations to feel the scale. Imagine lighting a city for an instant with the power a star emits in days. Then compress that energy into a snap shorter than the blink you use to picture it. The only way to make something that intense and that brief is to marshal ordered, coherent emission from a very compact engine, the kind of extreme environment where magnetic fields, rotation, and dense plasmas can move together like an orchestra with no stray notes. The sky serves these bursts in two temperaments. Some appear once and vanish forever. Others return in clusters or seasons, as if the engine has windows of activity. One repeater even shows a regular cycle of loud weeks and quiet weeks, hinting that something in its environment, perhaps a wind, a companion, or a wobble, opens and closes a gate. When the signal reaches you, it is already a story, and reading it is a craft. You measure how the lower radio tones lag behind the higher ones to estimate how much free, thin gas lies along the path. That quantity, called the dispersion measure, grows with distance and with the density of intervening material. So a very large lag tells you the source sits far beyond our galaxy, out where intergalactic space does most of the combing. On your spectrogram, you sometimes see each burst split into sub-bursts that slide downward in frequency over time. A sad trombone shape that hints at structure inside the engine or the plasma close to it. You might also see a broadening tail, as if rough patches along the way smeared the signal by scattering. And you can measure how strongly a magnetic field twisted its polarization, the rotation measure, to learn whether the source lives in a stormy, magnetized neighborhood. To turn sparks into places, you need position. And single-dish telescopes are like big ears that can tell you a note was loud but not which window it came from. Arrays of smaller dishes fix that by acting as a single, giant eye, triangulating the burst with sharp timing so you can drop a pin on a host galaxy, check which kind it is, and see whether the source sits in a region of vigorous star birth or in a quieter suburb. That leap from there was a spike to it, came from this exact patch in this specific galaxy, changed the game. Because it let astronomers tie some repeaters to dwarf galaxies with bright nurseries and others to more ordinary hosts. A diversity that says FRBs are a phenomenon, not a single mold. The leading engine in the deck is a newborn or newly restless neutron star with a magnetic field so intense that it can twist its own crust. A fracture or a sudden rearrangement can dump energy into its magnetosphere and drive a radio flare. And the clincher for this story was a 2020 event in our own galaxy, when a known magnetar spat out an unusually bright radio burst at the same moment it flared in high-energy light. A matched pair that proved at least some FRBs can come from Magnetar. But proof of one pathway is not proof of only one pathway. Some one-off bursts are so energetic that they push the Magnetar model to extremes, suggesting either very young, very charged up sources or entirely different engines, giant pulses from swiftly spinning neutron stars. Shocks where a fast wind plows into surrounding debris, or, in rarer cases, interactions in tight binaries where orbits and winds modulate the view. You can test these ideas with careful listening. Repeaters often show more complex structures, narrower features that drift in frequency and high variable rotation measures that imply knotted magnetic neighborhoods, while apparent non-repeaters might simply be faint repeaters you haven't watched long enough. That's why new surveys stare at the same sky patches for months, catching families of bursts from the same address and building a personality profile for each source. The beauty of FRBs is not only in their engines, but in their utility. Every burst is a backlight that turns invisible matter into measurable delay. So, with a large enough map, you can weigh the thin gas between galaxies. The ordinary matter that seems missing when you only count stars and cold clouds, sand show that it lurks in warm, sparse filaments that thread the cosmic web. You can also probe the outer halos of galaxies the signal passes through and compare how rough or smooth they are, how magnetized, how turbulent, turning each event into a core sample of a place you will never touch. In time, a network of hundreds or thousands of well-localized bursts can trace a 3D weather report of intergalactic space, one that changes with redshift and environment. Instruments built for this work have their own personalities. Some, like wide sky scanners, trade sharp positions for sheer catch rate, netting bursts by the hundreds and painting the statistics of energies and shapes. Others, with finer angular resolution, collect fewer but pin them to exact homes. The work you need to connect source to setting. In the minutes after a detection, telescopes across the spectrum swing to the coordinates, looking for afterglows or companions. Most FRBs leave no lasting light behind in other wavelengths, as if the burst is the whole show. But a few sit near steady radio sources that may be nebulae powered by the same engine. reservoirs that trap and remix energy over longer times. If you're tempted to jump from strange to alien, the better lesson is stricter and more satisfying. Natural engines you can motivate from known physics already make enormous, coherent radio flashes, and they live in the very places where you expect violent star-forming regions seeded with young neutron stars, or dense neighborhoods sculpted by past explosions. And while it's healthy to keep an open mind, it's wiser to let the data earn extraordinary claims rather than spending your wonder too early. What you should take with you is a way of thinking as much as a list of facts. Look for consistency across methods. Let variety be a clue rather than a nuisance, and use the path, not only the source. As an instrument, the universe is generous with probes if you learn to treat every beam of light as both messenger and measurement. So let the introduction be the quick, hooker cosmic knock on the radio door that lasts 1,000th of a second. Let the development unfold in calm detail, how the delay of low tones reveals distance and gas, how arrays fix positions and hosts, how repeating and non-repeating personalities point to magnetars and perhaps other engines, and how each burst doubles as a ruler and a thermometer for the space between galaxies. And let the conclusions settle like a slow breath. Most signals in your life are long and obvious, but sometimes the sharp ones teach you more. And if you learn to listen to what passes in an instant, you can reconstruct entire journeys from the way a note arrives late, the way it twists, the way it softens. And in that patient listening, you turn a fleeting spark into a map of everything it crossed. Tabby's star, a flickering sun no one can fully explain. Trust a star long enough and you start to believe light has manners. But then you meet Tabby's star and watch that belief unspool as the brightness dips arrive with no rhythm you can set a clock to. Sometimes shallow, sometimes yawning to nearly a quarter of the light gone, lasting days, 2 weeks, shaped like teeth, plateaus, and asymmetric slides that refuse the tidy script of a planet crossing a star. The way this puzzle surfaced is its first lesson in how science really works. Citizen volunteers in the Planet Hunters project flagged the Kepler light curve as wrong in an interesting way. Tabitha Boyajian and colleagues looked closer, and the community turned a curiosity into a worldwide campaign whose only guarantee was that reality, not rumor, would set the rules. The early facts tightened the mystery instead of solving it. There was no stable, repeating period the way a planet transit would show. The star itself looked like an ordinary, slightly hotter than Sun main sequence F star with no explosive tantrums. And space telescopes that see heat found no big excess of warm infrared glow, the kind of dust signature you'd expect if giant amounts of hot debris were circling close. In so whatever was blocking the light was either not warm or not abundant or not where you first imagine it. Then came the color clue that changed the temperature of the conversation. When the star dimmed again years later and telescopes jumped on it in multiple wavelengths at once, the fade was gentler in red light and stronger in blue, the exact kind of chromatic dimming that ordinary dust causes when it scatters shorter wavelengths more effectively. A truly solid, opaque object, like a planet or a massive engineered panel, would darken all colors equally. But these dips were biased, as if we were peering through clouds of fine grains. Those grains, however, introduced a second problem. Small dust so close to a star should heat up and glow in the infrared, and the observations didn't show the kind of bright, warm fog that would make a simple picture easy. The way out is nuance. Not fantasy dust can be cold if it spends most of its time far from the star, and only occasionally crowds the line of sight, or if it's continuously replenished in thin streams that never pile into a thick, hot ring, or if much of it sits in clumps at distances where sunlight is weak enough to keep the grains chilly. You also have to think about where the dust lives. Some models place it in a broad, tilted cloud bound to the star, perhaps the shredded remnants of an icy body or exomoon torn apart by tides. Others put it in the space between us and the star, a stray veil in the interstellar medium that just happens to cross our view and carries magnetic fields and grain sizes that imprint the same color bias. Still others imagine swarms of exocomets thrown inward from a distant reservoir, each one trailing a plume that briefly steals light and then disappears into silence. The sky offered more handles, subtle changes in specific absorption. Features like sodium or calcium hinted that gas sometimes joins the dust during dips, as you'd expect if icy or dusty fragments were vaporizing as they passed through sunlight. And careful checks of the star's spectrum during quiet times found it unremarkable, not acting like a star with large, long-lived cool spots that could explain deep, irregular dimming. Even the long-term behavior added texture. Archival plates and precision space photometry suggest that beyond the short, dramatic dips, there may be gentle, month-to-years changes in baseline brightness, small secular fades and recoveries that, if real and not an artifact, point to processes that evolve rather than repeat in line with drifting, replenished dust rather than clockwork eclipses by a single companion. Because the human imagination loves shortcuts. The alien megastructure headline roared early, but the data slowly denied it the oxygen it needed. The dips are chromatic like dust, not grey like opaque panels. Radio and optical searches for narrowband technosignatures came up empty. And the simplest accounting says you do not need extraordinary engineering to produce a handful of irregular, dusty curtains in a stellar neighborhood that likely holds leftover rubble from formation. The more interesting frontier is not what Tabby's star probably isn't, but how to use it to learn things you didn't know you could measure. Every well-observed dip becomes a laboratory for grain-size distributions, for how quickly grains are destroyed by stellar light, for how gas and dust travel together, for whether fragments arrive in clusters or as solitary and for how an F-type star's immediate environment evolves long after planets have settled into their lanes. Instruments and strategies have adapted to that promise. Automated alert networks watch for a new fade and whip telescopes across the globe into synchronized action so that, for the crucial hours, you get color information, polarization checks that reveal how aligned grains are, high-resolution spectra that can catch breath-thin gas lines, and deep infrared looks that might finally catch a whisper of warm dust if a cloud wanders too close. Between dips, patient monitoring of the baseline asks whether the star is truly dimming on timescales of years, or whether the apparent trends are the kind of slow, instrumental drifts that vanish under better calibration. One of the most quietly powerful outcomes is how localization, pinning the dips to the star and not some background contaminant, has pushed modelers to propose physically specific scripts. A recent collision among outer system bodies that kicked a long arc of debris into a grazing path. A disintegrating, loosely bound object that sheds fresh dust each periastron pass. A misaligned, puffed-up ring of grains shepherded by a small, unseen companion. Or an intervening interstellar sheet whose tiny changes in density and magnetic alignment produce the right color-dependent screen. Each scenario makes real, testable promises about which wavelengths should dim most, how gas lines should breathe in and out, how the timing should clump, and how the star should look just before and just after a deep event. Through it all, the tone you should keep is calm and curious. It is better science to recognize when a problem sits at the intersection of several modest effects: dust production, grain survival, orbital geometry, viewing angle, than to demand a single dramatic cause. The reason Tabby's star earns attention is that it forces you to instrument your patience, to admit uncertainty without losing grip, and to refine the difference between what's ruled out, what's merely disfavored, and what remains in the game. So let the introduction be the jolt that a respectable, ordinary star can misbehave in ways your tidy categories didn't predict. Let the development be the careful work-color-dependent dips that point to dust, the missing warm glow that constrains where that dust can live, the occasional gas signatures that support active shedding, the absence of periodicity that argues against simple transits, and the global observing campaigns that catch the brief windows when the sky lets you ask the right questions. And let the conclusion be a soft but sturdy lesson in method. You don't have to choose between wonder and discipline, because the best way to honor a mystery is to collect enough clean, diverse evidence that the set of possible worlds narrows all by itself. And when you finally close the page on Tabby's star for the night, you carry a deeper habitreat anomalies as teachers. Listen in more than one color, and remember that sometimes the honest answer is dust, arranged strangely. And that is not a disappointment, but an invitation to map the strange more precisely the next time the light steps down. Oumuamua, the first known interstellar visitor we saw. You don't expect a messenger to arrive after the conversation has already started. But that's how the first interstellar visitor we ever recognized announced itself in October 2017. Not as a slow approach with time to prepare, but as a hurtling object already past the sun, already on its way out. Discovered by a Hawaiian survey and given a Hawaiian name, Oumuamua, Scout, a fitting label for something that slipped through our neighborhood, just long enough to raise precise questions we're still learning to ask well. The first solid fact was its path, not the closed loop of a comet or asteroid bound to our star, but an open, forever leaving curve whose speed exceeded what the sun could hold. Proof that this body came from another system entirely. The second fact was the silence of traditional science-deep images found no obvious hazy coma or tail, even though its track skimmed close enough to be warmed, which immediately set it apart from the showy comets we know. With only a few weeks of useful light to work with, astronomers squeezed every drop of information from the way its brightness rose and fell as it spun, and the light curve said something dramatic. The object's shape or surface reflectivity must be extreme, because it brightened and dimmed by an amount larger than typical solar system bodies, as if you were watching a baton or a flat chip tumble and flash egon, then phazon, then egon again. Exactly which geometry fits best is still debated, long and thin like a shard, or wide and flat like a pancake. But the key point is that it wasn't a polite sphere. Its spin wasn't polite either. The rhythm drifted, as though Oumuamua were in a mild tumble rather than rotating cleanly around one axis. A behavior that makes sense for a piece that has been bumped and jostled over ages between the stars. A tumble also complicates how sunlight warms the surface and how any gases might escape. Details that matter for what came next. When teams modeled the trajectory very carefully, they found that gravity alone couldn't account for the motion. There was a tiny extra push away from the sun that faded with distance, roughly like the intensity of sunlight. A clue you can understand without formulas, because it's the same kind of curve that governs many heated things in space. The normal explanation for such a push is outgassing molecules sublimating from warm ice act like microscopic thrusters, but that raised the rub. Where was the usual comet spray of dust and familiar gases in the data? That tension lit the creative part of the field, and several sober possibilities took shape. Perhaps Oumuamua carried volatile ices that are hard to see from Earth once released. For example, formed in the ice by cosmic rays and liberated when warmed. Or carbon-bearing species that escaped efficiently but in amounts too low for our hurried telescopes to catch. Perhaps the surface had been sun-baked and space-weathered for so long that a crust formed, letting only small puffs leak through, enough to nudge the path but not enough to draw a classic tail. Perhaps the object was unusually porous, like a compacted snowbank of dust grains with lots of empty space between them. So that radiation pressure, that gentle push from sunlight that is real, but usually tiny, had a slightly larger effect than we expect on denser rocks. There were bolder suggestions, too, including the idea that Oumuamua might be a fragment of exotic ice chipped off a world like Pluto, or even an ultralight sheet capable of riding sunlight more like a sail than a stone. Those speculations were valuable mainly because they forced careful accounting. Could such material survive the long trip? Could it form in the numbers required? Would it have eroded away? What signal should it have left in our spectra? Why did we see none? Through this back, one anchor kept us honest, a second interstellar visitor to I. Borisov. Arrived in 2019 and behaved like a perfectly ordinary comet from an extraordinary place, with a clear tail and familiar gases, telling us that interstellar isn't code for weird so much as varied and shifting. Oumuamua, from a one-off miracle to the first surprising data point in a broader population we're just beginning to sample. If you want to understand what made Oumuamua educational rather than just entertaining, focus on method. With almost no time and very little light, astronomers used three simple tools: motion, brightness, and color, to infer origin, shape behavior, and physical processes. Then tried to break every favorite hypothesis with the hyperbolic path nailed the external origin. The extreme and drifting light curve demanded a non-standard geometry and rotation state. The missing coma restricted the kinds of ices and dust behavior that fit, and the small non-gravitational push insisted on some mechanism that couples to sunlight. Even the mundane details teach. Light reflects differently at different angles, so our estimate of shape depends on how much of the glinting geometry we caught during that short window. Tumbling can smear out or sharpen those changes, which is why some models tilt toward a wide, thin body while others allow a long, narrow one. Tiny amounts of gas can be invisible in hurried spectra, especially if released in small pockets rather than one grand fan. And porous materials can be surprisingly responsive to sunlight, especially if they're not held together by strong gravity. Behind the specifics lies a human lesson in pacing. We did not have to lean on extraordinary stories to keep the wonder alive. Ordinary physics, applied in careful combinations, is already strange enough when your sample size is 1 and your clock is ticking. Most likely, Oumuamua is a fragment of something that used to orbit another star, knocked free by gravitational shoving in its home system and tossed into interstellar drift for perhaps millions of years, before our survey finally met it at the end of a long arc. Its surface was altered by cosmic radiation and micrometeoroid hits. Its interior preserved some volatiles or a delicate structure, and its brief warm-up near the sun let either gases whisper out or sunlight push just a little harder on one side, tipping the trajectory by exactly the amount we measured. The story isn't closed because better data could still favor one family of models over the others. And that's why the future matters. The new generation of all-sky surveys will spot these visitors sooner, while they're still inbound, giving us time to take spectra, to map the spin more cleanly, to catch any faint comas, and, eventually, to send a fast, small spacecraft to ride alongside one and turn inference into detail. Until then, the cleanest conclusion is also the most beautiful. A single speck, heard for only a few weeks, is enough to test how you weigh evidence when no single clue is decisive. It encourages you to keep multiple working pictures alive without drifting into anything goes. To use the way a signal fades with distance as a ruler, the way brightness flickers as a yardstick for shape and spin, the way the absence of dust is information, not a void. Let the introduction be the surpriser scout already departing before you even knew to look. Let the development be the disciplined reading open path confirming interstellar origin. Extreme light curve, implying unusual geometry and tumble. A gentle extra push that asks for outgassing or sunlight's pressure, and the lack of a showy tail that narrows the options. And let the conclusion rest softly but firmly. Mystery here is not an invitation to fantasy, but a training ground for attention. And when the next messenger appears, you'll recognize it faster because this first one taught you how to listen, how to measure, and how to let several honest possibilities sit on the table until the sky itself decides between them. The wow signal, a one-time radio shout from the sky, begin with a pencil mark in the margin, because sometimes the universe knocks so softly that the first proof it happened is a human hand, circling a few characters on paper. On August 15, 1977, at Ohio State's Big Ear Radio Telescope, a volunteer named Jerry Emmon spotted the sequence in the printout code the system used to denote a sudden, strong spike in one narrow channel near the famous hydrogen line end. He wrote "wow" beside it, a small exclamation that later named the most intriguing one-time radio shout we've ever recorded from the sky. The setup was simple and quiet. Big Ear drift scanned as Earth turned, letting the sky pass through to adjacent beams like two flashlight cones. Anything fixed in the heavens would brighten for about 72 seconds as it slid through a beam, fade as it passed out, and if it was truly celestial, reappear a few minutes later in the second beam with the same bell-shaped rise and fall, while anything from a plane or a truck or a transmitter nearby would tend to smear across channels, pop up at odd angles, or repeat in places that made no astronomical sense. The wow signal did two things worth losing sleep over. It was astonishingly narrow, concentrated in a bandwidth far thinner than natural radio noise usually allows, and it sat almost exactly where many SETI searchers quietly hoped to find a hello, the neighborhood of the 21-centimeter hydrogen line, a universal frequency that water molecules and stars whisper around and that international agreements reserve for astronomy, making human interference less likely. On top of that, its strength rose and fell just as you'd expect from the telescope's fixed beam shape as the sky drifted by. A polite curve rather than a jagged accident. Yet it did not show up in the second beam, and despite nights and years of listening by Big Ear and later observatories, no signal with the same coordinates and behavior ever returned, which is where the one-time part bites. A beautiful single note with no encore. Enough to establish that something unusual happened, but not enough to settle what. The honest way to tell the story is to line up the possibilities and test them like recipes, not headlines. If it were a terrestrial transmitter, why would it sit in a protected band, appear in only one of two adjacent beams, and follow the beam's time profile so neatly? If it were a natural celestial process, what phenomenon produces such an incredibly narrow line and then never repeats? If it were reflection, say, a ground signal bouncing off space junk, why was there no parallel hit in other beams or channels? And how did the reflection mimic the precise timing expected of a source fixed on the celestial sphere? Over the decades, serious alternatives have been proposed and, importantly, checked. A suggestion that hydrogen clouds around comets passing through the field might have amplified radio light near the hydrogen line was testable. So observers measured comets and their environments and found emissions far too weak and too spread out in frequency to match the original spike. Ideas about distant satellites or aircraft fall down on the protected allocation and the clean beam-shaped rise. Even the narrow-band maser, thought nature's microwave laser faces trouble, because astrophysical masers are narrow but typically broader than the channel that lit up, and they usually come from star-forming regions or evolved stars you can revisit, not a region that stubbornly stays quiet. What makes the WOW signal so educational is that it forces you to learn the craft of radio astronomy rather than just the romance. The 6 EQUJ5 characters are not a code for messages, but a scale of intensity. The instrument printed as letters when the signal-to-noise rose above certain thresholds. The telescope's two-beam design was a built-in lie detector. A signal is genuine and celestial. It should paint the same shape in both beams as the sky turns. The band choice near hydrogen wasn't a hunch, but a long-standing SETI strategy. A quiet window where a sender might reasonably choose to place a beacon that any curious civilization could guess. And the absence of frequency drift across the 72 seconds, a detail often debated, depends on how the receiver tracked the sky and how the frequency channels were. Define technical minutiae that matter more than any sci-fi flourish. There is also a geographic lesson buried in the coordinates. The likely sky position lies in Sagittarius, near a star called Chi. But because the signal was seen in only one beam, and because big ears, exact tuning, and pointing had small uncertainties, we do not have pinpoint accuracy, just a patch. Modern arrays with much sharper localization could, in principle, tie such a signal to an exact star, but they were not listening in that place at that time, and that mismatch between the instrument we had and the instrument we now wish we had is the sober heart of the mystery. What should you take away as solid rather than speculative is this: the WOW signal was a real, loud, narrowband event recorded by a stable system. It matched the time profile expected of a source drifting through a fixed beam. It sat near a frequency that smart, conservative search strategies have emphasized for decades. It was not accompanied by the usual telltales of local interference, and it has never been seen again from the same sky patch despite targeted campaigns. That list does not prove intention, but it does justify curiosity, and it teaches method. Treat the absence of repetition as data, not despair. Keep your standards for extraordinary claims high, especially when a single detection is doing all the lifting. And notice how many ordinary terrestrial hypotheses can be tested and thrown out without needing to reach for unlikely explanations. In the years since, SETI has matured into a patient, multi-pronged effort that would recognize a modern WOW with far more context, fast back-end recorders that save raw voltage streams for reanalysis, arrays that localize to arcsecond precision, automated cross-checks with aircraft, satellite, and spectrum databases, and coordinated follow-ups across observatories that can pounce within minutes rather than months. This is not romance either, it's just what careful listening looks like in 21st century science. And it means that the next time a narrowband shout arrives, we can tell you exactly which window it came from, whether it drifted in frequency the way a transmitter on a rotating planet might, and whether any light beyond radio winked in sympathy. Until that day, the wow signal remains a gentle teacher rather than a solved case. It loosens your grip on the idea that one detection must mean one grand conclusion. It shows how instrumentation and strategy shape what you can claim. And it reminds you that sometimes the right response to a mystery is to build better ears rather than louder stories. So let the introduction be Eamon's pencil, a small circle around a big surprise. Let the development be the careful scaffolding beam shapes, protected bands, narrow channels, tested alternatives, and the hard fact of not. And let the conclusion be soft but durable. You do not need to romance the unknown to keep it thrilling, because the honest version is already rich. Enough some nights, the sky gives you one clear syllable. And the smartest thing you can do is learn to design a conversation that will be ready if the next syllable ever follows. The Fermi paradox, why the universe seems so quiet. Ask a child's question with adult patience. If there are so many places to live and so much time to try, why does the galaxy sound so still, and why, after decades of careful listening and looking, do we keep writing no clear sign yet in the margin? That puzzle called the Fermi paradox is not a riddle about aliens as much as a stress test for our assumptions about life, intelligence, technology, and how far faint evidence can carry across light years. And the calm way to approach it is to build the argument from pieces you can hold without equations. Begin with the expectation, because that's where the tension starts. Our galaxy holds hundreds of billions of stars, many with planets, and a generous fraction of those worlds sit in zones where liquid water could endure. Even if only a tiny percentage sprouted life, and a tiny percentage of those climbed to tools and language, and a tiny slice of those learned to cross space as slowly as sailboats cross seas, you still get an impression that pioneers should have had time to spread, even if each leap took ages. At modest speeds, a wave of settlements could, in principle, wash through the Milky Way in a time short compared with the galaxy's age, which tempts you to expect footprints, transmitters, artifacts, anything, and yet the night remains politely quiet. Now pull that expectation apart and examine where it can bend without breaking physics. Maybe life is genuinely rare at the start because the jump from chemistry to biology is a narrow bridge that almost never completes. Maybe the jump from simple cells to complex cells, or from animals to intelligent culture, is even narrower. Maybe the jump from intelligence to durable technology is narrower still because many worlds get stuck in cycles. They can't stabilize runaway climate shifts, star-driven radiation events, or simple resource limits that end the technological phase quickly after it begins. This way of thinking collects under the name filters, and the most unsettling question is whether the main filter sits behind us or ahead of us. It's a sober framing, not a fatalistic one, and it turns the quiet sky into a hint about how cautious and long-sighted we should be. But rarity isn't the only lever. The paradox also weakens if you let go of a hidden assumption that expansion must be fast and loud. because the galaxy doesn't require it. A civilization might spread in a lumpy, stop-start pattern that stalls at empty regions where stars are far apart. Settlements might favor deep, long-term quality over fastest possible growth. Societies might learn that the safest way to share a galaxy is to stay small, local, and silent. And colonization may be less like a conquering flame and more like dew, appearing wherever conditions are right, but never forming a single, sweeping front. Add to that the mundane obstacles we rarely consider in fantasy's long-term governance, culture drift over millennia, the difficulties of keeping a scattered federation coherent, and it becomes plausible that even a widespread presence could be patchy, low profile, and almost invisible to a random, faraway observer like you. Then turn from them to us, because the quiet might be partly our own doing. The space of possible signals is a haystack with many dimensions: sky position, frequency, bandwidth, polarization, modulation style, time of day, time of year, repetition, schedule, power level, and we have sampled only a thimble of that haystack with sharp enough ears. We listen at some frequencies, in some directions, for some minutes, with instruments designed mostly to find natural radio sources, and our sensitivity drops fast for transmitters that aim tightly or that talk in short, rare bursts. Our watch has also been short by cosmic standards. A civilization's loud phase may last centuries or less before it shifts to fiber, tight beams, or communication methods we don't anticipate, which means to neighbors can miss each other by being loud at different times or by choosing channels that barely leak. Even if someone is transmitting a beacon, we might be off by a sliver in frequency, or simply not watching at the right moment. If they favor optical flashes, neutrinos, gravitational ripples, or spread spectrum techniques designed to hide from noise, our current habits could slide right past their presence. Meanwhile, searches for indirect signs, planet atmospheres with telltale chemical imbalances, or the waste heat of large energy user, just beginning to bite and have so far found nothing obvious. But nothing obvious is still quite different from nothing at all, and it mostly tells you that galaxy-sized engineering or Earth-like pollution at nearby stars is not common, which is itself a clean, useful result. Another possibility is psychological rather than technical. Maybe many civilizations, after tasting how fragile complexity is, choose policies that reduce their footprint: less blasting power, more local computing, fewer bright beacons, in part to avoid risks from unknown others. That may sound like fiction, but there are game theory reasons for quiet strategies when stakes are high and distances large, and a culture that spends most of its attention inward, in art, simulation, or carefully managed ecosystems, can be both advanced and almost invisible. You can also challenge the entire premise by asking if intelligence tends to radiate into space at all. Perhaps the default end state is not sprawling empires, but compact, self-contained habitats where most value is produced with minimal outward signal, where travel is slow and rare because there's little economic reason to move mass when information and fabrication suffice. In that view, the galaxy could be full of minds content to remain faint. There's a subtle bias you must keep in mind. 2. You exist on a world where technology reached radio because that is what it takes to ask this question. So your vantage point is guaranteed to be one where at least one path worked. That selection effect can trick you into treating your history as typical when it might be unusually lucky. None of these ideas solves the paradox on their own, but together they transform it from a contradiction into a program of work. Measure how many Earth-sized worlds truly sit in stable, long-lived habitable zones. Study the role of magnetic fields, plate tectonics, and moons in climate stability. Watch for biosignature gases on nearby planets and learn how geology and life can imitate each other. Expand searches for technosignatures beyond radio into disciplined, falsifiable surveys of optical pulses, narrowband lasers, quiet waste heat excesses, or industrial byproducts that no volcano can counterfeit. And, just as important, log every non-detection as data rather than disappointment, because constraints are the bones of understanding. Method matters. Design surveys that revisit the same targets across months and years so you're not fooled by rare schedules. Share raw time series and metadata so that another team can reanalyze an interesting hit. Build instruments that can instantly record the fine-grained shape of any candidate so you can tell hardware glitch from sky. And cultivate patience, because the relevant timescales are long and the signal may be softer than the stories you grew up with. What does all this teach you, practically and philosophically, without leaning on fantasy? First, the quiet is not proof of loneliness. It is a statement about our current reach, our narrow listening habits, and the many sensible ways a civilization could fail to cross paths with ours. Second, when you update assumptions about ease of life's steps, about motives to expand, about how signals assent the paradox thins into a set of questions, you can test with better telescopes and broader strategies. Third, the most rational posture is hopeful rigor. Act as if neighbors are possible and worth looking for. Improve your tools so that a true surprise will be recognized in seconds rather than doubted for years. And treat every constraint as a map of where to push next. So let the introduction be the honest itch. So many stars, so little noise. Let the development be the careful unpacking filters that may be rare. Expansion that may be gentle. Searches that are young and narrow. Strategies that reward quiet and new, concrete ways to look beyond our current habits. And let the conclusion land softly but clearly. The silence you hear tonight is not a verdict. It is a syllabus, and if you learn to read it with patience instead of panic, you'll find that the universe is already answering, just in a slower, subtler voice than the one you expected, inviting you to widen your questions until a reply has room to fit. The cosmic dark ages before the first stars ignited. Imagine a night so deep that darkness has no shadows, no stars to cast them, no galaxies yet assembled, only a thin, cooling fog of hydrogen and helium stretching in every direction after the first light of the early universe has faded from visible sight. This long interval, the cosmic dark ages, wasn't a drama of explosions but a patient rearrangement of matter. When gravity began to amplify tiny irregularities, gas learned how to lose heat, and the stagecraft for the first stars was quietly built in silence your eyes could never see. To understand this era without equations, picture 3 clocks ticking together. One clock tracks temperature as the hot soup from the beginning gives up its heat to the growing emptiness. A second clock measures clumping as invisible mass deepens shallow wells that ordinary gas can slide into. A third clock counts chemistry, because even with only hydrogen and helium, a few stray electrons can catalyze the making of molecular hydrogen, an efficient coolant that lets a small cloud shed energy and shrink further. Early on, the leftover glow from the beginning still kept the gas warm by frequent interactions. But as the universe expanded, those interactions thinned. The gas then cooled faster than the background light, And during the purest part of the Dark Ages, the atoms were neutral, the space was transparent, and yet it remained black to your eyes because no new sources were shining. Dark, however, is not the same as empty. Those slight over-densities, initial ripples just a hair denser than their surroundings, grew slowly, guided by a massive, unseen scaffolding that doesn't care about light. Gas fell toward these seeds, and the smallest successful gathering spots were not city-sized galaxies, but minuscule minulas, places only a few 100,000 times the mass of our Sun, where the first serious cooling could happen. Cooling is the difference between a cloud that puffs back out and a cloud that keeps falling, with nothing but hydrogen and helium. You need tricks, and the trick available then was molecular hydrogen, which forms reluctantly in a two-step dance, helped by those leftover electrons. Once even a little of it appears, it gives the cloud a radiator, letting the gas drop in temperature until the center becomes dense enough to collapse in earnest. Meanwhile, a story only radio ears can hear begins to write itself along a very specific line of sound. The 21-centimeter whisper from hydrogen's internal compass flip. Long before any stars exist, collisions between atoms in the thickening clumps can slightly tip the alignment of those internal compasses and make the gas leave an imprint against the older background light. Not a glow your eyes would catch, but a faint, broad shadow across radio wavelengths that encodes the temperature and density of the primordial fog. As time drifts forward, collisions become too rare to keep that imprint strong everywhere. The signal weakens, waiting for a new coupling agent. That new agent arrives with the first trickle of starlight, because the earliest stars send out a special color that can once again link hydrogen's internal compass to the gas, temperature reigniting the shadow, and then, as young galaxies add high-energy light that warms the gas, flipping the radio signature from a cool absorption dip to a gentle emission. Glow before the hydrogen is finally broken apart and the universe loses the fog entirely. A later chapter called all of that fine structure to fade, the rekindling. The flips what makes the Dark Ages scientifically irresistible. It offers a way to take a three-dimensional picture of the universe before the first visible lamps turned on, to watch how clumps gathered, how the earliest sources affected their neighborhoods, and how the quiet became a chorus. Observationally, though, the task is brutal. The signal you want is buried under bright foregrounds from our own galaxy and from human technology, and the atmosphere itself bends and scrambles low-frequency radio waves. That's why teams build vast arrays of simple antennas in deserts and plateaus, why they calibrate out every glint of terrestrial noise, and why some dream of placing a radio observatory on the far side of the moon where Earth's chatter cannot reach. Two complementary strategies share the work, single instruments that listen to the whole sky at once, hunting for the global up-and-down shape of the Dark Ages and cosmic dawn curve, and sprawling interferometers that use the spacing between antennas like a camera's aperture to make crude but improving maps of how different patches of the sky brightened or dimmed relative to the ancient glow. There have been tantalizing hints, deep dip reported by one experiment, patterns whispered by others, but each claim must survive ferocious tests of calibration and foreground modeling. And the field has learned to prefer slow certainty over fast headlines. The reward, if done right, is a direct movie of structure formation rather than a reconstruction from later fossils. The theory side has matured, too, adding details that neither romance nor despair after the early glow faded. The gas and the unseen mass did not move in perfect lockstep, and that small streaming velocity between them can delay the growth of the tiniest clumps in some regions and enhance it in others, painting a subtle mottling onto the Dark Ages map. The first sources were likely enormous, short-lived stars with no heavy elements, so their light carved irregular bubbles in the neutral gas, and their deaths seeded the earliest metals that later cooling pathways would use. Because there were no dust grains yet to block or redden light, and no bright galaxies to confuse the view, the Dark Ages are the cleanest laboratory for certain questions. How does gas behave when gravity is the only architect and the chemistry set is almost empty? How does a background as smooth as the sea at midnight grow a landscape rugged enough to host everything you will ever see? How do the earliest heaters soft starlight and harder X-rays from newborn remnants, cooling to set the timing of the first dawn? Even instruments aimed at other goals help. Spectra of very distant quasars show a sudden saturation of absorption by neutral hydrogen just before the universe fully clears, a signpost that the fog was still thick not long before the first cities of stars took hold. High-resolution simulations that start with careful physics and no fudge factors predict a staggered birth, with quiet basins lagging behind faster-forming ridges, and that patchiness is precisely what the next generation of radio maps hopes to catch. You don't need dates to feel the sequence. Glow fades. Darkness clarifies. Ripples steepen. The first coolants switch on. The smallest wells fill. A few lights finally appear and, by shining, change the rules for everyone else. Then the fog lifts, and the familiar sky galaxies, clusters, web scums into view. What should you keep from this, beyond a new label for a quiet time? First, Dark Ages is not a placeholder for ignorance. It's a specific physical regime with testable signatures and a disciplined plan to reach them. Second, the absence of visible light is a feature, not a failure, because it lets a single, well-understood transition in hydrogen act as a universal tracer of temperature, density, and motion, turning the most common atom into a survey instrument. Third, the first stars did not appear out of nowhere. They were the logical end of cooling and clumping that started in darkness and preceded by rules you can describe plainly. Gravity gathers, gas cools, chemistry enables, radiation responds, and the feedback loop begins. Let the introduction be the hook that darkness here is not emptiness, only unlit potential. Let the development be the gentle, concrete path from neutral, transparent fog and collisional whispers, through the careful struggle for cooling, into the first scattered lamps that flip the radio sign and begin to clear the mist. And let the conclusion be a soft, practical thought. If you learn to listen where eyes fail, you can hear a universe building the conditions for everything that follows. And that habit, wading through the quiet, tuning your instruments, trusting subtle signals, will serve you far beyond cosmology. Because some of the most important beginnings in life also happen before any light is visible. First stars, huge, short-lived giants we've never directly seen, begin with a light you will never see directly. The first stars were not gentle sparks, but blistering blue furnaces born in a universe that had never known metal. And because their lives were short and their neighborhoods were sparse, they ended before any eye could witness them, leaving behind only the fingerprints of their fires and the consequences of their endings. To learn them, you don't point a telescope at a single object. You learn to read the aftermath, how pristine gas broke pattern, how certain elements appeared in odd proportions, how very young galaxies carry a voice that sounds like heat without the usual harmonies of heavier atoms, What made these stars different wasn't magic. It was the chemistry set, with only hydrogen and helium available. Cooling was clumsy, so the gas clumped into larger, hotter fragments than in later eras, making a top-heavy nursery where many stars were tens to hundreds of times the Sun's mass. Their surfaces would have been searingly hot, pouring out ultraviolet light that could peel electrons from atoms across vast neighborhoods and carve bright, ionized bubbles into the neutral fog, and their cores would have burned through their fuel with reckless speed, ending in just a few million years, the lifetime of a tree compared with the geologic age of a forest. Their deaths were not uniform, and those differences matter because they write the clues we can still find. A star on the lighter end for this era might have collapsed and exploded in a way that left behind a black hole and sprinkled space with a modest blend of carbon, oxygen, and heavier elements. On the very heavy end, some could have died as parent stability supernova, a special blowout where the star disrupts itself completely and leaves no remnant, producing a telltale even number excess in the elemental recipe more of certain nuclei than their odd neighbors, and the heaviest of all could have skipped the fireworks, collapsing straight into massive black holes that later growth would turn into the engines at the centers of young galaxies. None of this is poetry only. The chemical archaeology in our own galaxy's halo carries the evidence. A handful of ancient, iron-poor stars show extreme enrichments of carbon or unusual patterns among magnesium, calcium, and their cousins, fingerprints that match models of early, faint explosions that mixed their innards gently into the surrounding gas. These long-lived relics are quiet recorders, and when you plot their element ratios, you can back out the nature of the furnaces that fed them. Much like tasting soil minerals to infer which volcano exploded upriver centuries ago. We also listen for their chorus in young galaxies where the average stellar population is still raw. Spectra of the earliest star-forming systems sometimes hint at an unusually strong helium line with little accompaniment from the usual metal lines, as if the light is coming from stars so hot that helium is energized while heavier atoms are too scarce to sing back. Gravitational lenses occasionally magnify such galaxies enough for us to take a closer look, and although no single case closes the book, the pattern blue colors, extreme line strengths, sparse metal signatures keeps nudging the same direction. Meanwhile, the first dust born in the winds and deaths of these giants changed the rules of starbirth for everyone who came after. Dust grains provided new ways to cool the gas, allowing later clouds to fragment into smaller pieces so that the next generations included long-lived, sun-like stars, the kind that can hold planets and patience. In this way, the first stars were both a beginning and an ending, slamming the door on their own kind while opening 1,000 windows for quieter lights. Another subtle clue is the timing and shape of the universe's great unmasking. As these giants switched on, they began to rayonize the surrounding hydrogen, and the patchy geometry of that process, the size of the bubbles, how fast they overlapped, how cleanly the fog cleared depends on how many ionizing photons the first stars produced and how they were arranged. Large radio arrays, now being built and refined, aim to map that transition, not by seeing the stars, but by seeing how the leftover hydrogen responded. A landscape painting made from the negative space around lamps we cannot resolve. On smaller scales, we are learning that these first births were not one-offs confined to a single moment. In sheltered pockets far from busy neighborhoods, clouds of nearly pristine gas may have survived long enough to form isolated, latecomer first stars, even after the broader cosmos had moved on. which means the search is not limited to the very edge of visibility, but includes rare islands that carry yesterday's conditions into a later sea. Instruments like the newest space telescopes sharpen this hunt in three complementary ways. They find galaxies at extreme distances with colors and line features consistent with very primitive populations. They spot candidates magnified by intervening clusters so faint details become measurable. And they provide precise targets for ground-based observatories to dissect with deep spectroscopy, looking for the clean lack of heavy element lines and the signature helium glow that together whisper metal-free. Even so, the honest headline remains: we have not yet directly imaged an individual first star. And we may never do so in isolation, because distance, brief lifetimes, and crowding conspire against single pixel portraits. What we can and do capture are ensembles, echoes, and the scatter of elements in the oldest stars. The ratios in early galaxies, the way hydrogen lost its electrons in lumpy waves, the mass distribution of the earliest black holes, of which act like traces in a fluid that otherwise runs clear. The practical questions that flow from this are anything but abstract. How top-heavy was the first generation, were most of them monsters? Or did a minority of smaller ones survive long enough to be hiding, dim but present, in the outskirts of ancient clusters? How quickly did their radiation shut off further metal-free births in their own neighborhoods? Did the star formation happen in tiny groups or in dense knots with feedback that choked itself off? And which death channels dominated? Because that choice changes how fast the universe gained the carbon and oxygen that chemistry and, eventually, biology. In this early regime, details cascade. Faster rotation in a primitive star can stir its interior and drive powerful winds that seed its surroundings even before it dies. A slightly different background of X-rays from newborn remnants can preheat or pre-ionize gas far away, changing when the next round of clouds can cool. And the strength of small relative motions between gas and the unseen. Mass can tilt the balance between one big clump and several small ones, altering the entire timetable of first light. Through all of this, keep the tone of disciplined wonder. The first stars are not a fairy tale. They are a solved-for variable in an equation you can inspect from its outputs. And the discipline is to insist that every candidate's signature survive cross-checks helium without metals, element ratios matching a specific kind of explosion, young galaxies whose light budgets make sense without smuggling in later-era physics. What should you carry away that makes you wiser, not just dazzled? First, the universe's first lumps were likely enormous, hot, and brief, not by accident, but by the cooling limits of a metal-free gas. And that choice set an initial condition for everything that followed. Second, their legacy is everywhere, even in your body. The carbon in your cells, the oxygen in your lungs, the calcium in your bones owe their earliest abundance to those few, fast lives, which means you are a late chapter in a story that ran its prologue in blue fire. Third, the way we study what we cannot see is a method you can use outside astronomy-read consequences. Rather than demanding perfect views, weigh patterns across independent clues, prefer a small set of converging hints over a single loud claim, and keep models on a short leash that the data holds. If you let that settle, the structure of this lesson is quiet and clear. The hook is that the first stars have never stood alone in any telescope's field. The development is the chain of reasoning primitive chemistry forcing massive births, expected temperatures and lifetimes, distinct explosions producing unique elemental recipes, early galaxies and radio maps acting as proxies. and the conclusion is a soft instruction in patience sometimes. The most important actors leave the stage before the audience arrives, and your job is to reconstruct the play from the heat left in the seats, the glitter on the floor, and the new language that later voices learned to speak because the first ones burned so brightly for such a short time. Gamma ray bursts, the most violent flashes in the cosmos, start with a sky that blinks harder than any storm you've ever imagined. For a heartbeat to a few minutes, a patch of space erupts in gamma rays light so energetic it can shred molecules. Then the fury fades, leaving a cooling echo that slides down the spectrum through X-ray, ultraviolet, optical, and radio. These are gamma ray bursts, and they are not mere explosions, but directed catastrophes. Pencil-thin jets launched from engines pressed to their limits, visible across most of the observable universe because they concentrate power the way a blowtorch concentrates heat. The cleanest way to understand them is to separate the flash from the aftermath and the who from the how. The flash, the prompt emission is the first spikes satellites see. A ragged train of peaks that can jitter like a strobe or burn as a single, smooth pulse. And buried in that pattern are clues to the engine. The light is often polarized, suggesting a structured magnetic field. The highest energy photons arrive close in time to the rest, implying that the outflow must be racing outward at a significant fraction of light speed so that matter and light inside the jet don't destroy each other in a fog of self-made radiation. And the overall spectrum is broader than a simple hot surface, pointing to a mix of processes collisions within the outflow. Magnetic reconnection that snaps and releases stored energy, and radiation leaking from deep within the jet's photosphere, where it first becomes transparent. The aftermath, the afterglows, the slow, useful teacher, as the jet plows into the thin gas between stars. It launches a shock that accelerates electrons and lights up the environment in predictable colors. And by watching how that glow fades hour by hour, you can infer the jet's opening angle, the density of the surrounding medium, and whether the outflow carries more normal matter or more magnetic structure. Sometimes the light curve takes a sudden step downward, a jet break that tells you the beam is narrow and is now widening as it descends. And that single bend converts an impossible energy budget into a sensible one once you account for beaming. The true energy is high but not absurd. On the who question, nature offers at least two families. Long bursts, the ones that can last tens of seconds or longer, tend to live in the bright knots of star-forming galaxies and are frequently followed by a supernova, whose spectrum shows nothing heavy in its outer layers, a signature of a massive star that lost its envelope before death. In that picture, the core collapses to a black hole or a newly born, highly magnetized neutron star. An accretion disk forms from the falling debris, and twin jets punch their way out, drilling through the dying star and escaping to space, where they radiate as the prompt flash. Short bursts, often under 2 seconds, prefer older neighborhoods as well elliptical galaxies, or the outskirts of spirals, and a few have been caught with a faint, reddish glow from freshly forged heavy elements, the telltale of a merger between two neutron stars that flung out neutron-rich matter and, in at least one celebrated case, also sent a ripple in spacetime that our detectors felt. In that scenario, the coalescing cores form a compact engine and launch a jet, whose observed brightness depends on whether you sit inside the beam or off to the side, which is why some events look muted in gamma rays, but brilliant in the slower thermal light of the debris. Those are the headline tracks. But the family tree has branches, A handful of ultra-long bursts linger for thousands of seconds and may signal either a star so large that its envelope fed the engine for a long time, or a different beast entirely, such as a star torn apart by a black hole that sits in a mass range between stellar and supermassive. At the other end, low luminosity bursts in the nearby universe may be cousins powered by a shock wave breaking out of a star rather than a clean, highly collimated jet, which would explain their softer glow and the close match with supernova features. The detective work is multi-messenger by design. Space telescopes catch the flash. Networks of observatories on the ground scramble within minutes to catch the afterglow before it slips. Radio arrays keep watch for months to track the energy that moves from the jet into the surrounding gas. And, when we are lucky, neutrino and gravitational wave detectors listen in parallel to catch particles and ripples that can escape from depths light cannot reach. Those parallel channels sharpen the story in both directions. The absence of high-energy neutrinos, in clear coincidence with most bursts, limits how many are powered by the most efficient particle-accelerating shock scenarios, while the presence of gravitational waves in a few events nails down the compact merger origin without guesswork. Even the places where gamma-ray bursts choose to live are informative. Long bursts prefer small, chemically simple galaxies where massive stars lose less mass to winds, preserving the angular momentum and structure needed to feed a central engine. Short bursts are found both near and far from their host centers, a sign that their progenitor pairs receive kicks during earlier supernova and wander before their final embrace. And that diversity of offsets is a measurable logbook of how long they drifted. Because the jets are narrow, selection effects are everywhere. We only see the ones that point our way or whose wings are wide enough to brush past us. Which is why an event accompanied by gravitational waves looked faint in gamma rays. We were looking from the side and then brightened later in radio and X-rays as the jet's shocked cocoon expanded into our view. That geometry answers a common "how can they be so bright" worry on paper. An isotropic burst would require more energy than a star can muster, but no real event is isotropic. Their power is focused into a small, solid angle, which lets them be both physically reasonable in total energy and record-breaking in apparent brightness. What remains in healthy debate is the microphysics in the jet. Does the prompt light mostly come from internal shocks where faster shells overtake slower shells, or from magnetic fields rearranging and heating the flow, or from hot layers slipping free at the last moment they can escape? Does the afterglow show a single, clean shock or hints of reverse shocks that briefly light up the material moving outward? Do some engines launch jets that start as magnetic and become matter-dominated only later? Each of these options makes quantitative promises in polarization, spectral shape, pulse timing, and the way different colors fade, and every bright, well-observed burst tightens the screws on the answers. There is also the question of masquerade. Galaxies nearby host exotic flares from highly magnetized neutron stars that at great distances would look like very short bursts. Careful localization and context are how we avoid counting those as mergers, and the field now treats each candidate as an opportunity to prove its type rather than an excuse to rush a label. Beyond the astrophysics, gamma-ray bursts are tools. Their afterglows backlight the gas in and around their host galaxies, letting us measure the composition and motions of matter in the early universe. Their frequency and brightness distribution encode the history of massive star formation and the rate of compact mergers, and their extreme spectra let us test how intergalactic space dims the highest energy photons, which tells us about the diffuse glow of all the stars that ever lived. The practical takeaway for you is threefold. First, most violent here is not hyperbole but a statement about power per solid angle. When a jet points at you, it turns a distant event into a torch you can see halfway across the cosmos. And that visibility is why we can use these flashes as signposts in deep time. Second, there is no single origin story. Some are the deaths of massive, rapidly rotating stars. Some are the final union of city-sized corpses. Some are outliers that widen the family portrait. And learning which is a matter of disciplined forensics rather than guesswork. Third, the way the field moves forward, catching the first light within seconds, handing coordinates to a global community, stitching radio to X-ray to gravitational waves, and letting non-detections be as informative as detections is, a model for any hard problem, where the truth hides in fast changes and faint tales. Let the introduction be the simple shock that a universe can flicker like this. Let the development be the patient, layered reading prompt strobe. Afterglow map, long versus short families, beaming that makes the energy sane, environments that reveal ancestry, and new messengers that confirm the scripts. And let the conclusion land quietly. The violence you glimpse is not chaos but choreography. An engine pushing matter and fields into alignment for a moment so brief you could miss it if you blink. And if you learn to meet that moment with ready instruments and a cool head, it becomes more than spectacle. It becomes a ruler, a backlight, and a lesson in how attention turns danger into knowledge. Magnetars neutron stars with Unthinkable. Magnetic fields. Let a compass go feral in your mind. There are stars so intensely magnetized that space around them behaves like a strained material and light itself changes how it travels. And we call their remnant hearts Magnetar city-sized neutron stars, whose magnetic fields are so far beyond ordinary experience that Unthinkable is not flair, but a practical warning about intuition. The way they come to be is a lesson in stacked extremes. A massive star exhausts its fuel and its core in the first seconds after collapse. The newborn neutron star is hot, fluid, and spinning fast. And turbulent motion couples with rapid rotation to amplify seed fields into titans, likely weaving a hidden toroidal field deep inside and a poloidal field that threads outward, like steel cabling anchored in a crystalline crust only a few kilometers thick. Everything in a magnetar is dense, to absurdity a teaspoon would outweigh a mountain, and everything is structured. Neutrons in the inner layers behave as a protons become superconducting, and the outer solid crust forms an ultra-rigid lattice that can store stress from the interior, field the way a bent bow stores tension. Nearer the base of that crust, pressure crushes nuclei into exotic pasta-shaped sheets and spaghetti-like strands that alter how heat and charge move. This architecture matters because a magnetar's personality is not set only by rotation, as in a standard radio pulsar, but by slow, relentless rearrangements of magnetic stresses. As the buried field evolves, it shears the crust until it slips in a stark wake, and that crack suddenly twists the external magnetosphere, pumping energy into it like a snapped rubber band. The result is a flare of X-rays or gamma rays, sometimes a forest of short spikes, sometimes an intermediate roar, and on rare occasions a giant flare that briefly outshines everything in its galaxy before the system settles back, its spin having hiccuped and its magnetic wires slowly untwisting over weeks to months. You can tell a magnetar by its habits. It spins surprisingly slowly, seconds, not milliseconds, and Yet it loses that spin faster than ordinary neutron stars, as if a powerful brake were pressed. Its steady light is hotter and tougher than a cooling ember should be, because the very act of magnetic decay and rearrangement heats the crust from within. Its timing is noisy, punctuated by glitches and even rare anti-glitches, when the internal superfluid or the magnetosphere rebalances in an instant. And during outbursts, its spectrum hardens and then softens as the twisted field relaxes. A behavior consistent with charged particles upscattering surface photons in a magnetosphere suddenly thick with currents. In these environments, you get to test physics you can't build in a lab. The magnetic field near the surface can exceed the threshold at which quantum electrodynamics predicts the vacuum acts like a birefringent crystal, splitting light into preferred polarization. Photons can convert into pairs and back, or even split into lower energy twins under the right conditions. And the polarization of X-ray light from magnetars has now been measured at levels and angles that fit the picture of strongly magnetized transport, letting astronomers turn bursts and steady emission into practical experiments on how light and magnetism talk when fields rewrite the rules. A magnetar's neighborhood is as instructive as its surface. Many live in star-forming regions, consistent with the idea that only the heftiest progenitors, possibly spun up or merged in their youth, can seed fields this large. Some sit near massive clusters whose stellar census lets you estimate ages too young for ordinary cooling to explain their heat, pointing again at magnetic decay as a heater. One even orbits close to our galaxy's central black hole, proving these fragile-seeming objects can persist in rough gravitational company and letting us use its pulses to probe the soup of plasma and magnetic field at the heart of the Milky Way. Their energy can shape events far beyond the star itself. A newborn, rapidly spinning magnetar has enough rotational energy to power a superluminous supernova, and its declining spin can leave fingerprints in the light curve. In other circumstances, a newly formed magnetar might launch an ultra-narrow jet that contributes to some of the most luminous high-energy flashes we see, while older, restless magnetars can, on occasion, fire off millisecond radio bursts from tangled magnetospheres. Brief radio syllables that won't make sense unless you know that magnetic crusts can crack and reconnect like storm fronts. Observationally, they are found first by their tantrums. Spaceborne monitors catch hard flashes and send coordinates. X-ray telescopes then watch the glow fade, mapping hotspots that march across the surface as the star turns. Radio dishes sometimes hear pulses that switch on only after an outburst, as if new open-field lines have carved temporary channels. And high-precision timing reveals how the torque changes as the external twist relaxes. A practical measure of magnetic topology you can track without ever seeing the field directly. In the quiet between storms, their steady light and pulse shapes let us model how heat leaks from the crust, how that heat is funneled by strong fields toward the poles, and how the conductivity map of the star evolves as the lattice heals and the internal field drifts. Put across a population, those patterns sketch a magneto-thermal life cycle: youthful, hot, and bursting; middle-aged, cooling, but still cracked; older, calmer, with fields that have partially decayed and crusts that have grown less often. Theory keeps pace by turning difficult microphysics into testable macroscopic behavior. Hall drift reshuffles, field lines in the crust like sliding tiles. Ohmic diffusion slowly bleeds energy into heat, and embedded toroidal fields can store stress that only decades later find a way to the surface. In some models, pockets of superfluid neutrons pin and unpin to the crustal lattice and act as a second reservoir of sudden change, explaining why spin can jump when light flares two coupled systems announcing the same release. There are open questions worth your attention precisely because they are concrete. What mixture of internal toroidal and external poloidal field best matches the observed timing and flare statistics? How strong are the fields in the core compared with the surface we infer? Do all magnetars begin with the same vast energy budget and then diverge only by geometry and environment? Or are there genuinely distinct birth channels? When a flare reconnection runs wild, how deep does the crack reach, and how much does it reshape the star's future behavior? Can strong field crustal modes ring long enough and hard enough to launch faint gravitational waves that next-generation detectors might hear? Each of these questions has a path forward: extrapolarimetry to pin down geometry, longer timing baselines to map torque noise, wide field monitors to catch the earliest seconds of new outbursts, radio follow-ups to see when and why transient pulsations wake up, and population studies linking magnetars to their birthplaces to weigh the progenitors that made them. What you should carry with you is not only a portrait of a cosmic oddity, but a method. A magnetar is a natural laboratory where matter under crushing density, a lattice on the edge of its strength, and a magnetic field beyond terrestrial imagination interact in ways we can read through light, timing, and polarization. If you learn to let multiple kinds of evidence cross-check each other, how hard the spectrum is, how the pulse drifts, how the polarization swings, you can convert awe into measurement without giving up the wonder that pulled you in. So let the introduction stand as a simple hook that in some corners of the sky magnetism becomes a shaping force, not a footnote. Let the development bring carefully new knowledge, birth by dynamo, crust and superfluid interiors, starquakes and untwisting magnetospheres, quantum effects that turn vacuum into a medium, environments that reveal ancestry, and instruments that turn tantrums into diagnostics. And let the conclusion land softly but clearly. The strangest stars are not fairy tales. They are tools, and when you meet a magnetar in your thoughts, you are meeting a place where the universe lets you watch strength fail, rules bend, and light carry the report faithfully back across the dark. Neutron-star mergers, collisions that forge heavy elements. Hold a piece of gold up to the light and try to imagine its birth, not in a furnace like the sun, but in the crush of two dead stars spiraling together. Their city-sized cores made of neutrons packed so tightly that a teaspoon would outweigh a mountain. Their orbit shrinking as they shed energy in ripples of space-time until, in the last seconds, tides tear at their crusts and the stars merge into one violent engine. That is a neutron-star merger, and it is one of nature's most efficient factories for the heaviest elements in your life. The story begins long before the crash, with a pair of massive stars born together. Each lives fast, detonates as a supernova, and leaves behind a neutron star. Kicks from those explosions jolt the pair, but if gravity keeps them bound, they settle into a long, tightening dance that can last longer than civilizations and sometimes carries them far from their birthplaces into the quiet outskirts of a galaxy. As the orbit decays, the final minutes are a lesson in extreme physics you can picture without equations. The stars raise tides on each other that stretch and heat their outer layers. The very fabric of space-time rings faster and louder, a chirp that observatories on Earth have now recorded from multiple mergers. And just before contact, The stars begin to shed neutron-rich matter into tidal tails and into a hot, swirling disk that will become the launch pad for everything that follows. What follows is not just a flash, but a sequence of ejections and transformations that each leave their own signature. The fastest sling outward along the equator in thin, crescent-shaped sheets. Dynamical ejector, launched by tides and shocks that are spectacularly rich in neutrons. A bit later, winds blow off the hot accretion disk, and from the temporary remnant, their composition tweaked by neutrinos, so that some of this material is still neutron-heavy, while some is a touch more balanced. The remnant itself may survive for a brief time as a hypermassive neutron star, supported by fast spin and intense magnetic fields, or it may collapse quickly into a black hole. And that choice alters how much extra matter the system can expel. Inside every gram that gets away, atomic nuclei begin a rapid series of captures and decays. The process climbing the periodic table into the lanthanides and actinides that no ordinary star can forge in bulk. Those newborn nuclei are unstable at first, and as they relax, they leak heat into the expanding debris, powering a short-lived glow called a kilonova. The color and timing of that glow are not poetry, but chemistry. Lanthanides have a forest of electron transitions that make the ejector astonishingly opaque, thousands of times more so than iron-rich supernova debris. So light struggles to escape, and the emission turns deep red and infrared over days. If a portion of the outflow is less neutron-rich, because neutrinos from the remnant shifted the balanced in for a brief window, you get a faster, bluer component that peaks early before the redder curtain takes over. With coordinated telescopes, you can watch this color handoff, map how fast the light fades, and back out how much mass was thrown out, how opaque it was, and therefore which parts of the factory dominated tails, shocked plumes, or disk winds. Sometimes, a narrow jet also punches out along the poles and lights up the distant universe as a brief, high-energy flash. But because jets are needle-thin, most mergers will hide that drama from us. The kilonova and the gravitational waves are the reliable, democratic messengers that don't care where you sit. The mergers are not just fireworks, they are laboratories. The subtle imprint of tides on the gravitational wave chirp reveals how squishy neutron stars are. From that we infer their radii and put pressure on competing models of matter at densities no experiment on Earth can reach. The total mass and how long the remnant resists collapse hint at the maximum mass a neutron star can support before becoming a black hole. The brightness and color of the kilonova, combined with late-time radio and X-ray afterglows from ejector plowing into interstellar gas. Let us reconstruct the geometry of the outflows and ask whether magnetic fields or neutrinos did most of the sculpting. And when we can identify the host galaxy and measure its redshift, while the gravitational waves give us a distance directly, a merger becomes a standard siren, a clean, independent tool for measuring the cosmic expansion without relying on any ladder of intermediate calibrations. If you step back from a single event and look at the galaxy as a record keeper, the evidence that mergers forge heavy elements is written in old stars like notes in the margin. Some of the most ancient iron-poor stars in the halo of our Milky Way carry huge enrichments in europium and other R-process elements. A pattern that doesn't trickle in over many small sources but arrives in big, rare doses, the kind a single merger could deliver to a young, small galaxy. In a few tiny dwarf galaxies, an entire population of stars shares the same R-processed fingerprint, as if a lone collision long ago spiked the gas and then many stars formed from that enriched cloud. Chemical evolution models that include neutron star mergers reproduce these patterns when they allow for a wide range of delay times. Some mergers happen quickly after star formation. Others take their time, consistent with the idea that these factories operate across environments and eras. The details matter because they tell us how diverse the factories are. A merger that collapses promptly to a black hole ejects less material and produces a dimmer, redder kilonova. One that leaves a long-lived, ultramagnetized remnant can pump out extra energy and wins, biasing the outflows toward a brighter, bluer, early glow. Ejecta launched in the equatorial plane tend to be more neutron-rich, and so heavier in lanthanides, while polar winds see more neutrinos and carry lighter R-process If a jet forms but we view it off-axis, radiolight may rise slowly over weeks as the jet's cocoon expands into our line of sight. Even the places mergers happen teach you something, because earlier supernova kick the progenitor stars. Many pairs drift for ages before merging, so short-lived afterglows often appear far from the bright centers of galaxies, in thin gas that makes the radio rise slow and clean. In clusters of old stars, close encounters can build new pairs dynamically, giving the universe an alternate channel to feed the factory long after star formation has faded. Open questions are concrete and testable. How often do mergers happen compared with the rates at which galaxies need our process enrichment? What mixture of dynamical ejecta and winds dominates in different environments? Do some mergers overproduce the heaviest actinides, while others stop short? And can we read that in the detailed spectrum of kilonova? How stiff is neutron-rich matter, really, and what does that stiffness imply for the fate of the remnant? Can we catch the earliest seconds of a kilonova, often enough to map the blue-to-red transition with statistical confidence? And can we measure polarization to learn how clumpy the ejecta is? The roadmap is already under construction. Wider and faster surveys to catch the first hours of light. Radio arrays that keep listening for months. Gravitational wave detectors with sharper ears that will pin down distances and masses with smaller errors. And coordinated strategies that can point optical, infrared, X-ray, and radio telescopes within minutes to the same fading ember. What you should carry out of this, steady and practical, is threefold. First, the atoms that make up your jewelry and your electronics and part of your blood's chemistry likely condensed in the fallout of these collisions, not in ordinary stars. Second, mergers give us rulers for the universe and yardsticks for matter at densities beyond any lab, turning awe into measurement. Third, the method that makes sense of the multi-messenger listening, disciplined modeling, and a refusal to let any single channel tell the whole story is the same method that turns other overwhelming problems into solvable ones. The hook is the gold in your hand. The development is the factory you now know how to sketch binaries born. Orbits tightened, tides raised, matter thrown out and cooked into heavy nuclei. Light shaped by chemistry and geometry, waves in space-time carrying the invoice and the conclusion is a soft, durable thought. Not all creation is gentle. And yet from the briefest, most crushing unions come the slow, useful elements of our long lives. Every time you notice the weight of a ring or a coin, you are feeling the quiet memory of two collapsed stars agreeing, for an instant, to manufacture something that could last. Gravitational waves, ripples in space-time from distant catastrophes, start with an idea. You can feel in your hands, twist a rubber sheet and let it go, and a ripple races outward carrying the story of the twist. Now replace the sheet with spacetime itself, and the twist with a distant, violent change in gravity. And you have gravitational waves, not sound, not light, but traveling distortions in the geometry that tell you what moved, how fast, and how deep the struggle ran before the universe smoothed itself again. The cleanest way to learn them is to think like a listener with several instruments tuned to different octaves. In the high notes, laser interferometers on Earth, vast L-shaped machines with arms kilometers long, watch for changes in length so small they amount to a fraction of a proton over the entire span. They do it by bouncing light back and forth between mirrors hung on exquisitely isolated suspensions until any passing ripple makes one arm effectively shorter while the other gets longer, changing the pattern of light where the beams meet. That tiny telltale would be hopelessly buried in noise if not for a toolbox that feels more like music production than astronomy. Multi-layered seismic isolation to hush Earth's tremor. Ultra-polished mirrors, cooled and coddled to keep thermal jiggle down. Vacuum pipes to stop air from smearing the phase. Lasers stabilize so hard their frequency barely wanders. And even squeezed light. A quantum trick that reshapes the uncertainty in the photons to push down the hiss that would otherwise drown out the whisper. When the whisper arrives, it usually doesn't come as a simple bump. It comes as a chirpan oscillation that rises in pitch and amplitude as to compact objects whirled faster, lose orbital energy to waves, and finally merge. The shape of that chirp is a readable sentence. It encodes a combination of the masses, the way the spins tilt or align, and whether one partner is tidally distorted before the end. Put more plainly, the pattern tells you if you've just heard two black holes coalesce, two neutron stars embrace, or a mismatched couple fall together. And it lets you weigh and age the system without seeing a single photon. Spread detectors across the globe, and the slight differences in arrival times let you triangulate a patch of sky. Add polarization information. Weigh the stretching and squeezing are oriented, and you test whether gravity's waves have exactly the two patterns Einstein's theory predicts or sneak in extra. Modes that would betray new physics. Drop to lower notes, and you need different ears. In the midband, a space-based interferometer will one day fly its arms, millions of kilometers apart, to hear the leisurely inspirals of black holes tens of thousands of times the sun's mass. The slow dance of compact binaries in our own galaxy, and perhaps the hum of relics from processes that shaped the early universe. The reason to go to space is practical. Earth is too loud and too small to host such long strings of light. Sink lower still, to periods of years. And you must borrow clocks from nature. Arrays of millisecond pulsars, neutron stars that sweep radio beams past Earth like metronomes are, timed so precisely that any correlated rhythmic slippage in their arrival ticks across the sky betrays a background of waves washing through the galaxy, most likely from the giant black hole pairs that live in merging galactic cores. This is the base of the gravitational wave symphony, and learning to hear it turns the whole sky into one continent-sized detector where each pulsar is a marker and the correlations between them are the signal. Across these bands, the science is richer than spectacle. For black hole mergers, you are finally probing gravity in its strongest, most dynamic regime. The ring down the way the remnant settles after the crash comes in specific tones set only by mass and spin. And matching those tones is a sharp test of whether the object is the simplest black hole allowed by general relativity or something stranger. For neutron star mergers, the early part of the chirp carries a faint signature of how icily each star deforms. a window into the stiffness of matter at densities no lab can replicate. The waves also arrive almost exactly with any accompanying light, letting you compare their speeds across cosmic distances and verify that gravity and light share the same limit to exquisite precision. For supernova, the hope is to catch an as-elusive burst from deep inside a collapsing star, a jitter in the core that neutrinos can hint at but only waves can map, turning a once opaque process into an observable engine. For lone neutron stars, the target is a continuous tone from a minuscule mountain or a wobble on their crust, a signal so faint that it will take patient, narrowband listening to bring it above the floor. Yet a detection would weigh the star's asymmetry and test how solid its surface truly is. And then there are the carpets beneath the solos, stochastic backgrounds that add up many unresolved sources into a gravitational hiss, which you can analyze statistically to learn the average lives of black hole pairs, or perhaps to limit exotic early universe phenomenophize transitions, cosmic strings that might have scored the first minutes of cosmic history with their own wave trains. The method that extracts knowledge from these ripples is practical rather than mystical. You calibrate interferometers by literally pushing on the mirrors with radiation pressure and checking that the instrument's measured motion matches the known nudge. You stitch together banks of template waveforms calculated on supercomputers so the data stream can be matched in real time, the way a song recognition app finds a tune in a noisy bar. You share alerts across the world within seconds so telescopes working in light can pivot to the right patch of sky if there is something to see, while radio arrays and X-ray eyes keep watch for slower after. You replay the same data with different assumptions, allowing, for instance, for slight deviations from Einstein's equations, turn the absence of any detectable mismatch into clean constraints. The kind of no that actually tightens the yes of a theory's allowed room. You also use distances from the waves themselves because the amplitude, after you account for beaming and orientation, declines with how far the source is to build standard sirens, independent yardsticks for the expansion of the universe that do not lean on a ladder of astrophysical objects. The frontier is wide and specific. Make the detectors quieter at low frequency by taming ground motion and Newtonian noise from shifting air and soil. Press down quantum noise at high frequency with better squeezing and brighter, more stable lasers. Coat mirrors with materials that jiggle less. Coordinate with radio timing arrays to map the nanohertz sky. Plan the spaceborne detector's orbits so that its changing geometry encodes polarization and direction as the constellation turns, and push supernova simulations to be faithful enough that when a burst is finally caught, the imprint can be read as a blueprint rather than a Rorschach. What should you carry out of this, beyond the thrill of a new sense? First, gravitational waves are not metaphors. They are measurable changes in shape that pass through you and your instruments, and their detection turned gravity from a static backdrop into a broadcast channel. Second, the signals are not single-purpose fireworks. Each chirp, hum, or hiss is a layered report on the nature of compact objects, on the behavior of matter at crushing density, on whether the universe allows extra polarizations or faster-than-light gravitational messengers, on how galaxies grow their central monsters, and on the expansion of space itself. Third, the posture that makes the field succeed build different ears for different octaves. Combine information from many messengers. Prefer patient calibration over dramatic claims is a template for learning anywhere that reality speaks softly. Let the introduction be the hook that space can ripple and you can feel it. Let the development be the calm, structured tour How interferometers hear chirps. How pulsar clocks reveal a background. How spaceborne arms will open the mid-band. How each source family writes a distinct waveform. How precision and cross-checks turn whispers into measurements. And let the conclusions settle like a slow breath. Once you know that the universe is not only seen, but also heard, you start noticing that some truths arrive as gentle stretches and squeezes, and that attending to them quietly, with good instruments and better habits, lets you learn from catastrophes without being anywhere near the harm. Wormholes, theoretical shortcuts through space and time, begin with a corridor you can't yet build. Imagine walking into a room, taking 3 slow breaths, and stepping forward only once, yet arriving light years away because the floor itself has been folded so that 2 distant tiles now touch. In physics, that corridor is the idea of a wormhole. Not a hole in space, but a specific geometry where distant regions share a hidden throat. And the honest thrill is that the equations we used to describe gravity do allow such shortcuts, while also warning that keeping them open is far harder than sketching them on paper. The development starts with a calm picture you can hold without symbols. Gravity, in modern language, is geometry shaped by energy and momentum. Draw a map with hills and valleys instead of forces, and particles simply follow the straightest lines the map allows. Ordinary masses make gentle valleys, inexact solutions of the same equations. More adventurous landscapes appear bridges and tunnels that connect separate patches. The earliest bridge was a non-traversable one, like a cul-de-sac that pinches, closed before you can pass. Later, researchers wrote down traversable versions, careful metrics, whose throat stays open in principle, then asked the practical question: what kind of stuff must sit in the throat to stop geometry from collapsing back on itself? The answer is where fantasy meets discipline. You'd need matter with pressure and energy arranged so that, along certain rays of light, the effective energy density is negative. This does not mean anti-gravity dust you can scoop with a net, but it does mean the material allowed by classical intuition won't do, and quantum fields must take the stage. Quantum theory admits small, temporary pockets of negative energy, famously between very close metal plates in the Casimir setup, and more generally in carefully prepared squeezed states of light, but nature strictly rations them. The more negative you want, the shorter you may keep it. And these quantum inequalities act like budget rules that keep you from paying for a highway with coins meant for a bus fare. That tension is healthy. It pushes the next layer of questions. Could a wormhole be supported if you gather many tiny negative contributions and balance them with positive ones? Could the back reaction of fields you use to prop the throat undo your work? And can any arrangement survive the jostling of passing travelers or ambient radiation without snapping shut? Even if you dodge those constraints, stability is unforgiving. A traversable throat tends to focus light and matter in ways that amplify small disturbances. As anything falls in, its energy adds curvature, which can narrow the passage. Tidal forces may be tame in some designs, but brutal in others. Incoming light from the universe can blue shift and heat the throat, and all of those stressors must be managed for longer than a heartbeat to call the structure usable. This is why modern research splits in 2 productive directions. One path stays astrophysical and asks, if wormholes exist in the wild, how might we notice? Would they lens background stars like ordinary masses, or leave telltale differences, bright spots where a black object would cast a shadow, peculiar amplification patterns in microlensing surveys? unusual timing delays for light that passes through the throat and returns, or distinctive echoes in the ringdown of space. After a violent event, none of these hints has been seen convincingly, but they're concrete targets for future instruments. The other path is theoretical and, lately, increasingly computational, in strongly curved toy universes used to test ideas about quantum gravity. Small deformations or couplings between two systems can make information flow in a way that looks, in a dual description, like a signal traversing a short wormhole. Tabletop teleportation through a wormhole experiments fall into this camp. They are not holes in our spacetime, but engineered quantum circuits whose math mirrors the rules of a safe, traversable passage in a simplified world. Those studies are valuable because they teach how negative energy appears and how it's bounded, how signals avoid being scrambled into noise, and which features of the geometry are essential versus decorative. They do not claim a portal in the lab, but they do sharpen our language for what a portal would demand. Time travel enters here as a cautionary edge case rather than a promise. In simple thought experiments, moving one mouth of a traversable wormhole fast or parking it deeper in gravity makes the two ends age differently. If you then connect them again, some paths through the throat close on themselves in time. Great story until you add quantum fields, whose response to such loops tends to explode and backreact in ways that likely shut the construction down before paradoxes take root. A pattern summarized as chronology, protection, and best treated as a guardrail rather than a law. Topological censorship theorems add another restraint. Under broad, classical conditions with sensible energy, observers following reasonable paths cannot access shortcuts that change the connectivity of space, which is a precise way of saying, if you want a traversable wormhole, you must violate the usual energy bookkeeping somewhere. That might sound like a hard no, but it is really a specification. If a future theory of quantum gravity quietly relaxes some energy conditions in controlled ways, the door reopens. If it does not, then wormholes remain mathematical galleries, beautiful, instructive, and non-architectural. Observational patience is our best friend while the math matures. Precision surveys of the sky already collect the kinds of data that would flag a blatant lensing oddity. Horizon-scale images of compact objects can test whether every dark silhouette is truly a one-way sync or whether any shows signatures of a throat. Gravitational wave catalogs grow each year, and analysts are learning to search the leftover vibrations for weak, structured late-time tails that some exotic geometries predict. Even the absence of anomalies is useful, because it corrals speculation into smaller corrals and pushes designs toward those that either leave no trace or are ruled out. For personal orientation, you can keep three truths side by side without conflict. First, wormholes are not mere fiction. They are legitimate solutions to the equations we trust in every other gravitational context, and studying them clarifies how geometry and energy police each other. Second, traversable versions require ingredient-sustained negative energy and robust stability that we do not know how to assemble at useful scales. Quantum effects grant you small coupons, then snatch them back, and back reaction tends to collect interest. Third, there is still practical value in the chase. By asking what a safe shortcut would need, you end up measuring vacuum fluctuations more carefully, designing cleaner polarization experiments, mapping lensing statistics with finer combs, and building detectors that could catch footprints of any exotic compact object, wormhole or otherwise. So let the introduction be a simple hook, a hallway where the tiles touch because space itself folds. Let the development be disciplined rather than dreamy, geometry as gravity, throats that require negative energy, quantum budgets that limit how long you can spend, stability that fights you, astrophysical tests that would notice a misbehaving lens, and quantum information toy models that teach which features matter. And let the conclusion exhale softly. You do not need to promise travel brochures to keep wonder awake. Wormholes already earn their keep as precise questions that force better measurements and sharper theories. If shortcuts exist, the same caution that built our best instruments will eventually find their fingerprints, and if they do not, the search will still have taught us to listen more cleanly to both light and vacuum, to separate beautiful possibilities from usable paths, and to respect that in a universe ruled by geometry, some rooms connect only on paper until deeper rules say otherwise. White holes, hypothetical opposites of black holes. Imagine a cosmic fountain that refuses to drink, instead of a place where light and matter fall inward and never return. Picture a region from which stuff can only rush outward, a one-way mouth that spits but never swallows. This is the white hole. Not a discovered object, but a precise idea that falls out of the same equations that give you black holes. When you run them backward in time, a reminder that physics sometimes offers mirror images even when nature prefers just one of the pair. The development begins with geometry rather than hype. In general relativity, a black hole is defined by an event horizon that no signal can cross outward. Reverse the film and you get a horizon no signal can cross inward. A past singularity whose debris streams outward into the universe. When you extend the simplest black hole solution to its full mathematical map, a white hole region appears as the time-reversed twin of the familiar future-trapped region. And in that extended atlas, the two are connected by a non-traversable bridge that closes too quickly for travel. That much is clean math. The hard question is whether real processes can ever make such a thing. Collapse under gravity leads to black holes because you can start with ordinary matter and let it fall. To make a white hole, you would need to arrange the universe so that, in the past, the right stuff appeared at a singularity and expelled itself along a perfect schedule, an initial condition so contrived that it violates the spirit of formed by evolution and instead looks like a cosmic stage direction. Even if a white hole were somehow set up, it would be exquisitely unstable. The horizon of a black hole is forgiving small. Disturbances fall in and are hidden, whereas the horizon of a white hole is a wall against which incoming perturbations pile up. Any stray photon, any grain of dust, any ripple from the outside gets infinitely blue-shifted as it tries to approach, and that injected energy collapses the structure back into an ordinary black hole when you run the full dynamics. So the slightest touch from the rest of the universe tends to destroy the only outward rule. Thermodynamics strengthens the case against astrophysical white holes. Black holes fit neatly with the second law by assigning them an entropy proportional to their area. An accretion plus radiation makes the total entropy of black hole plus environment climb. Time reversing that story to make a white hole would require the environment's entropy to drop in a coordinated way while the hole ejects organized. Low entropy matter possible on paper, but fantastically unlikely in a universe that started messy and keeps getting messier. Still, the concept is useful precisely because it sharpens what would be required of any shortcut around cosmic censorship and the arrow of time. If you ever thought the Big Bang might be a white hole, the comparison forces discipline our early universe was hot, smooth on large scales, and filled with nearly thermal radiation. Not the kind of sharply structured low-entropy jet a white hole would spew into a pre-existing spacetime. The bang looks less like a hole emptying into space and more like space itself beginning hot everywhere, which is a very different claim. Quantum ideas reopen a narrow door. Not for everyday white holes, but for effective ones. Some loop quantum gravity models and related proposals imagine that a black hole's interior bounce at ultra-high density could convert, long after formation, into an outward explosion that resembles a small, short-lived white hole Planck star scenario. In that picture, the event horizon would not be truly permanent. Information need not be lost, and the late-time outburst could, in principle, spray out debris that had been trapped. The catch is quantitative. To remain consistent with everything else we see, the timing, energy, and frequency of such bounces must thread tiny needles, and current observations have not demanded them. The most honest way to talk about evidence is to explain what we would look for and why we haven't found it. A genuine white hole acting in our sky would produce outflow without prior infall. An eruption with no feeding history, no accretion disk, and no gravitationally bound neighborhood announcing months of build-up. It might lens background stars like a compact mass does, but with subtle differences in how light curves drift as material pours outward rather than inward. It could, in speculative models, produce brief, bright flashes that are hard to reconcile with known engines. But then you must show why they don't also leave the telltale thermal or afterglow signatures that other explosive phenomena inevitably produce. Precision images of dark, compact objects near galaxy centers match the silhouette expected for horizons that only trap, not throats that expel. Gravitational wave ringdowns the dying tones after mergers so far sing the simple notes of black holes rather than the echo-rich patterns some exotic alternatives would imprint. And the statistics of high-energy transients can be explained with engines we already understand without calling in a new class of eruptors that never accrete. None of this makes white holes a mistake. It makes them a measuring stick. They teach you that reversing time in an equation is cheap, but reversing entropy in a universe is not. They highlight how horizons tolerate or punish perturbation. They clarify which energy conditions and stability arguments are doing the real work in theorems that bar traversable, shortcut geometries under ordinary matter, and they motivate clever searchers that would, if they found anything odd, force us to adjust those arguments carefully instead of vaguely. If you're tempted by maybe microscopic ones, quantum field theory does permit negative energy densities in small, fleeting pockets, and in principle, quantum gravity could create brief, tiny white hole-like outbursts, but the same quantum inequalities that permit them also starve them of longevity and size, making any macroscopic effect easy to suppress and hard to observe. The practical roadmap, then, is modest and concrete. Keep testing horizons with sharper images and deeper timing to see if any compact object refuses to behave like a sink. Comb lensing surveys for amplification patterns that ordinary compact masses cannot mimic. Model the late-time tails of gravitational wave events to set upper limits on exotic echoes, and treat outlier transients as opportunities to compare known engine predictions with white hole-like burst predictions in color, duration, and environment, letting the data choose without romance. Let the conclusion land softly but firmly. White holes hold your attention because they are the cleanest mirror of a thing you know exists. And studying why the mirror is hard to realize in nature teaches you more than a casual dismissal would about time's arrow. About stability, about how geometry polices energy, and about the difference between a solution in a book and a process in a world where dust drifts. Photons wander, and small interactions never quite equal zero. If someday an observation forces us to admit a controlled violation of our comfortable assumptions, the white hole will be ready as a vocabulary word to make sense of it, and if not, the search will still have paid for itself by teaching us how to tell a genuine fountain from every kind of clever mirror. Primordial black holes, tiny clues from the infant universe, begin with a shadow that could be older than atoms. Imagine a black hole whose birth certificate doesn't list a dying star, but a moment in the infant universe when space itself briefly crowded, enough to pinch into Attractor primordial black hole, a hypothetical relic formed long before galaxies, valuable not because we've seen one clearly, but because chasing them forces you to interrogate the earliest conditions with tools that reach beyond light. The clean picture is this: as the hot, expanding universe cooled, tiny ripples in density seeded by processes like inflation, phase transitions, or defects grew or faded depending on scale. If a ripple on a particular horizon scale was unusually steep, gravity could overwhelm pressure just as that scale entered causal contact, collapsing a patch into a black hole, whose mass was set not by a star but by the mass of the universe inside that horizon at that instant. That simple coupling between size of the fluctuation and mass of the whole is the map you need. Different early universe mechanisms would spike the fluctuation power on different scales and thus predict different preferred masses. So a census of allowed or excluded primordial black hole masses is a backdoor probe of the physics that operated when the cosmos was minutes, seconds, or even fractions of a second old. Evidence, so far, is a net of no's wrapped around a few honest maybes. If PBHs were extremely tiny, quantum mechanics says they would slowly radiate away through Hawking evaporation, leaking particles and high-energy photons that, integrated over time, would brighten the gamma-ray sky or leave characteristic byproducts in cosmic rays. The fact that the sky isn't swamped in such signals rules out many very small masses and, intriguingly, makes the boundary between already gone and still here a clean line you can draw without astrophysical guesswork. Move up in mass, and gravitational lensing turns into a key. Compact objects that drift in front of background stars or galaxies magnify their light in a way that depends on the lens mass. And wide surveys, watching millions of stars for little brightening, blips have excluded PBHs as the dominant form of dark matter across broad swaths from asteroid-like masses up through parts of the stellar regime because we simply don't see enough of those telltale peaks. Even the fastest flashes can help. A PBH with a mass billions of tons could femtolens a gamma-ray burst, imprinting a tiny interference pattern in its spectrum. The absence of those wiggles squeezes another band of possibilities. On yet larger scales, PBHs would perturb the orbits of wide binary stars, puff up the delicate star clusters in ultra-faint dwarf galaxies, and heat thin stellar disks. The fact that these structures persist narrows how many hefty wanderers can roam unseen. Then there's the quiet early universe itself, which acts like a sensitive microphone. PBHs that accrete gas in the pristine plasma era would have dripped energy into their subtly distorting the cosmic microwave background's smoothness and spectrum. The lack of those distortions pins down how many such accretors could have existed and how greedily they could have fed. Stitch all these constraints together and you don't get impossible. You get constrained with windows, narrow mass ranges, where, depending on assumptions about how broadly the mass distribution is spread, PBHs could still make up a meaningful slice of the dark matter, or at least exist in interesting numbers. Two windows keep showing up in careful reviews, one near lunar-like masses, where microlensing is trickier to deploy, and another in parts of the tens of solar masses neighborhood, complicated by selection effects and by the fact that ordinary stellar pathways also produce black holes there. That second window is where gravitational waves re-energize the conversation. Detectors have heard multiple mergers of black holes tens of times the sun's mass, some with spins so small and directions so random that PBH enthusiasts argue they fit a born cold, born unaligned origin better than the story of paired massive stars evolving together. Skeptics reply that dynamical formation in dense clusters can also yield low, misaligned spins. This is not a stalemate, a program, if PBHs contribute. The merger rate, mass distribution, spin distribution, and how those change with cosmic time must line up with a self-consistent population model, and every new detection tightens that cross-check. There is also a subtler, beautiful link between the early universe fluctuations that could make PBHs and a background of low frequency gravitational waves they would also generate. Sharp spikes in primordial curvature don't just collapse some regions. They also stir a bath of second-order gravitational waves whose pitch depends on the scale of the spike. Pulsar timing arrays are beginning to map a nanohertz hum in the sky, most plausibly from giant black hole pairs in galaxy centers. But some PBH-producing models predict additional or different signatures there, turning the whole enterprise into a two-messenger audit of the same physics. If you prefer your clues chemical rather than sonic, PBHs sizable enough to plant early seeds could help explain how supermassive black holes appeared so quickly in young galaxies. A PBH of a few hundred to a few thousand solar masses, formed from a large initial fluctuation, would give a head start to growth by accretion, reducing the need for finely tuned stellar pathways. But that idea must survive the same hurdles as all PBH stories. Don't overheat the microwave background. Don't overlens the stars. Don't over-disrupt the fragile. Even non-detections teach you where to look smarter next. Microlensing campaigns now push to shorter cadences to catch briefer events from lighter lenses. Strong lensing monitors of distant supernova and quasars search for millisecond echoes caused by tiny intervening masses. Fast radio bursts, which flash across huge distances, can exhibit telling interference if a small compact object sits along the line of sight. And surveys of the faintest dwarf galaxies use the survival of their coldest star clusters as sensitive accelerometers for any unseen bumps that wander through. On the theory side, the story is moving from could fluctuations be big to which specific early the mechanism can produce the right amount of enhanced power without overproducing PBHs or violating smoothness constraints on neighboring scales with inflationary models that briefly slow roll in a different way, or that create temporary plateaus leading the pack. In all such models, the mass function is extended rather than monochromatic, which matters because many observational limits were first reported for single masses and must be translated carefully to broad distributions. Through all of this, a disciplined posture keeps the romance honest. PBHs are tempting as a one explanation fits many idea dark matter, seeds for giants, odd gravitational wave mergers, But the data insists on modular thinking. Each proposed role needs a tailored mass function and abundance, and those choices ripple across entirely different If you stay with that discipline, the value is huge. Even if PBHs turn out to be bit players, you end up with sharper microlensing statistics, cleaner maps of the microwave background's fine texture, deeper timing networks of pulsars, and better models of how delicate structures survive in the outskirts of galaxies. So let the introduction be the hook that a black hole might predate stars. Let the development be the methodical tour formation from early spikes, evaporation constraining the tiny lensing and dynamics squeezing the middle, accretion and the microwave background policing the larger, gravitational waves and pulsar timing cross-checking the narrative, and focused search strategies on fast transients and delicate systems. And let the conclusion land softly. Primordial black holes are not a promise. They are a question shaped like an object. And whether the answer is few, some, or none, the act of asking makes you read the baby universe with finer eyes, replacing vague origin stories with tests that any honest cosmos must pass. The cosmic microwave background, afterglow of the Big Bang. Imagine opening a window not to a place but to a time, and finding the faintest, oldest light still crossing the room. The cosmic microwave background is that murmurant, almost perfectly uniform glow bathing the entire sky at about 3 degrees above absolute zero, yet tucked inside its smoothness is a speckled pattern of tiny, warm and cool patches that carry a full memory of how the young universe breathed before the first stars existed. And if you learn how to read those freckles, you can reconstruct a surprising amount of everything that followed. Begin with the moment this light became free to travel, when the universe was hot and dense. Light bounced constantly off a fog of charged particles. As expansion cooled the fog, protons and electrons finally paired into neutral atoms, and space turned transparent in a sudden shift, freezing in place a snapshot of temperature and motion that we now see stretched into microwaves by the long journey. That snapshot is more than a photograph. It's a sound recording made visible. Before transparency, gravity squeezed the primordial gas into wells while pressure pushed back, setting up waves that rang through the plasma-like vibrations on a drum. Where a wave was at the crest when the fog cleared, the patch appears slightly hotter. Where it was, in the trough, slightly cooler. The pattern of patch sizes is not random decoration, it forms a set of preferred scales, the acoustic peaks, whose relative heights and spacing encode specific facts, such as how much ordinary matter the universe contains, how much unseen gravitating matter was there to deepen the wells, and how fast the cosmic clock was ticking then. A single angular scale in that pattern acts as a standard ruler on the sky. When you measure its size with care, you learn the geometry of the whole stage, finding that space is very nearly flat on large scales, like a sheet that neither domes nor caves in. Because the glow is so uniform, variations are just a few parts in 100,000. You might think it says nothing about change, but it does. The largest scale ripples subtly brighten and dim as light climbs through evolving gravitational landscapes on its way to us, letting us test whether those landscapes have been draining or deepening with time. On smaller scales, the speckle blurs because thick regions smear out fine detail before the fog clears, a natural damping that confirms how photons carried heat across the plasma. Even polarization adds a verse to the story. The same last scatter that released the light also imparted a faint alignment to the waves. When you map that polarization, you recover the direction of the ancient flows that drove the acoustic beating. And you also see how matter, along the line of sight, has gently bent the paths of those photons on their way here. A lensing effect that turns polarization into a sensitive probe of the clumpy web the universe later grew into. One day we hope to find an even subtler polarization, curl pattern that would reveal ripples from the very beginning, an echo of gravitational waves imprinted well before any atoms existed, but for now the upper limits already teach caution and push instrument makers to tame every source of glint and glare a detector can invent. Method matters here as much as marvel. To pull the primordial message out of the sky, you cannot point a single thermometer and declare victory. You must observe the entire dome at many frequencies, because our own galaxy contaminates the view with dust that glows and electrons that spiral in magnetic fields. Each contaminant has its own color, so multi-band maps are how you separate local paint from ancient plaster. You calibrate using the dipolar clean, sky-wide gradient caused by our motion through the cosmic rest frame, which gives you a built-in yardstick for the instrument's gain. You cross-check one patch against its neighbors, because noise that clings to the ground or the spacecraft won't repeat with the same sky pattern. And you quantify an unavoidable limit called cosmic variance. The simple truth that you only get one universe to measure at these scales. So the largest features come with a fundamental statistical fuzziness no amount of patience can shrink. From this careful listening come concrete, durable lessons that guide the rest of cosmology. The spectrum of the glow is astonishingly close to a perfect black body, which is a precise way of saying the early universe was in near thermal equilibrium and that no later process dumped energy into the microwave background in a way that would scar its color. The fine-scale speckle nails down the density of normal matter and the ratio of matter to radiation at the time of release. The lensing signatures show how structure later grew, letting you weigh the combined pull of everything that can gravitate. The faint suppression of power on the very largest scales hints at our motion and at the finite patch of sky we can actually observe. Even clusters of galaxies leave their fingerprints by slightly boosting or dimming the background in their direction. As photons pass through hot, thin plasma bound to a cluster, they pick up energy from the electrons they scatter off. And that small spectral tweak lets you find clusters and measure their gas without needing them to shine on their own. No single map does all this. Instead, balloons, ground arrays in dry high places, and spaceborne surveys each contribute their strength. Some excel at fine detail, others at polarization, others at keeping a stable view for years, and the combined result is a consistency check as much as a catalogue. There is philosophy in this, but it is the practical kind. The microwave background turns the universe itself into an experiment done only once and read slowly. Rather than wishing for a laboratory you don't have, you design instruments that turn the sky into data you can interrogate. You learn to treat foregrounds not as a nuisance but as additional signals to model and subtract. And you accept that some uncertainties are baked into the fact that you cannot rerun the first 15 minutes of everything. For you, the takeaway is threefold. First, Afterglow undersells it. This light is not a fading ember, but a frozen pattern of the universe's first successful attempt at memory. A record of sound waves that let us weigh ingredients and judge geometry with confidence. Second, progress here comes from humility building, many maps at many colors, checking instrument against instrument, letting statistics, not desire, decide when a faint feature is real. Third, The practice of turning small differences into large truths, of letting a part per 100,000 contrast teach you the shape and contents of the whole, translates well outside cosmology. It's a habit of attention that prefers structure over spectacle. So let the hook be simple. An ancient light you can still detect where the backyard microwave horn sings a song from before the first stars. Let the development be the patient reading last, scattering as a curtain drop. Acoustic peaks as rulers and thermometers, polarization and lensing as extra verses, foregrounds as challenges that instruments and analysis can meet. And let the conclusion arrive softly, by learning to hear the universe's quietest broadcast. You find that certainty can grow from whispers, and that sometimes the best teacher is not a new explosion, but a very old glow that never stopped crossing the room. CMB cold spot, a strange patch of sky that's too cold. Begin with a bruise on the oldest light we know. When you unwrap the sky-wide map of the cosmic microwave background and let your eyes drift over its gentle freckling, there is one region that seems cooler than it should be. A broad, subdued patch framed by a faint warmer ring, like a thumbprint left on fresh paint. This is the CMB cold spot, and it is interesting not because it screams new physics, but because it forces you to practice the difference between a real anomaly and a lucky draw from a noisy deck, teaching you how to test ideas when the universe only ever deals one hand. The cleanest description starts without romance. The background glow is a nearly perfect, nearly random field of tiny temperature wiggles. And if you run millions of simulated skies with the same statistical rules, most of them will show a few biggish ups and downs simply by chance. So the first question is not what caused the cold spot, but how surprising is it, honestly, given the game we're playing? The answer depends on how you ask. If you decide in advance exactly which size, shape, and location to examine, and then find a spot that extreme, your eyebrows should rise. But if you scan the whole sky at many scales, use a filter that emphasizes round features, then pick the most dramatic circle you can find and christen it anomaly, you must pay a penalty the look elsewhere effect for the fishing expedition. Even after that sober correction, the cold spot keeps a small, non-zero claim to oddness, but it no longer yells. It whispers, asking you to check everything that could manufacture a cool patch without rewriting cosmology. Foregrounds come first in that audit. Our own galaxy paints, the microwave sky with dust emission and with electrons spiraling in magnetic fields, and galaxy clusters can tweak the background light as it passes through their hot plasma. But both culprits have color frequency dependence that lets you peel them away by comparing maps at many wavelengths. The cold spot, stubbornly, remains when you do that, a sign that it is not a smudge of dust or a cluster's imprint. Instruments are the next suspect. So you compare independent experiments with different hardware, scanning strategies, and error budgets. The spot appears in multiple datasets that were built to disagree if a glitch had made the mark, and that cross-check erases the easy escape hatch of detect a hiccup. With systematics and foregrounds cornered, you move to late-time effects that can cool background photons as they travel to us. Because the path to your telescope is not flat gravity, along the way can make the light lose or gain a little energy. The most famous of these is the integrated Sachs-Wolf effect. If a photon crosses a giant underdense region as supervoid while the universe's expansion is accelerating, the gravitational well it falls into on entry is not the same depth it climbs out of on exit. The mismatch leaves the photon ever so slightly colder. Galaxy surveys indeed reveal a sprawling underdensity roughly aligned with the cold spot on the sky. an enormous hole in the distribution of galaxies that looks like a plausible accomplice. But when you do the accounting, the numbers rarely add up. A void big enough and deep enough to explain the whole cold spot would need to be extreme, even by cosmic standards. And careful modeling says the observed underdensity can provide only a fraction of the temperature drop. That pushes you to options that sound less dramatic than headlines, but are more educational. Either the cold spot is a statistical fluke made memorable by human pattern-hungry perception and by a ring-like morphology, exaggerated by a particular filtering method, or it is a blensome chance fluctuation at last scattering, gently sharpened by a real but insufficient supervoid along the way. Because the spot's shape has that intriguing cool core and warm ring, theorists have not resisted more exotic guesses. A cosmic texture, kind of topological defect, seeded by symmetry breaking in the early universe could imprint a disk-like pattern with a specific temperature profile. This idea even makes a testable promise. How likely are you to find other, smaller siblings elsewhere on the sky with consistent statistics? Searches for such a family have not delivered a decisive yes. Another speculative proposal imagines a bruise from a collision between our inflating patch and another echo of a multiverse interaction which would paint a circular imprint with particular polarization features at its edge. The data so far show no compelling matching polarization swirl. Anisotropic Beyonce patterns, spiral-like flows in the early universe can be tuned to mimic large-scale anomalies. But when tuned to the cold spot, they tend to clash with the rest of the sky's exquisite randomness and with how structures later grew. Each time you chase one of these alluring detours, the discipline is the same. Write down clear predictions that go beyond "there is a spot." Check those predictions against independent parts of the data, and let the unfriendly answers teach you what to stop believing. Meanwhile, the cold spot has turned into a productive exercise in method. It forced the community to agree on how to score anomalies, to develop wavelet tools that compress just the right kind of localized structure, to build catalogs of supervoids and superclusters that can be stacked under the CMB to measure average late-time effects, and to sharpen the analysis of polarization and lensing maps that trace the mass between us and the background. It also trained a healthier habit of a posteriori caution. If you discover something by looking exactly where it is strongest, you must be humble about the quoted odds. Even if the ultimate verdict is mostly chance, you do not lose. You gain better foreground cleaning, improved simulations, and a clearer understanding of how rare shapes naturally bubble up in a Gaussian random field, when you are allowed to scan freely across it. For you, the practical takeaways fit in a small pocket. First, the cold spot is real as a feature in multiple sky maps, but real does not imply revolutionary. It is an invitation to quantify surprise properly, not proof of a hidden door. Second, the partial supervoid explanation is a case study in how astronomy often works. A phenomenon is rarely single cause, and careful contributions from independent effects, surly time ripples. Late-time gravitational changes can stack without any one of them being dramatic alone. Third, the right attitude turns even stubborn questions into progress by confronting a strangely cold patch. We learned to stitch together galaxy surveys and CMB data more tightly, to trust polarization and lensing as separate arbiters, and to value negative results that prevent clever stories from running ahead of measurements. So let the introduction be the hookah brews on the universe's oldest light. Let the development be a calm investigation, frequency checks to kill foregrounds, instrument cross-checks to kill glitches, void physics that helps but doesn't finish the job, exotic ideas that make specific promises and mostly fail them, and statistical honesty about how you counted your surprise, and let the conclusions settle softly. Sometimes the most useful mysteries are the ones that refuse to break the rules. They keep you honest, improve your tools, and remind you that wonder in science does not need a plot twist only, a willingness to read even the quiet, awkward places on the map as carefully as the beautiful ones. The Great Attractor, a gravitational pull with no clear source. Start with the feeling of a current you can't see tugging at everything you know. When astronomers measure not just how fast galaxies recede with the general expansion, but the small extra speeds they have on top of that. Thousands of those velocity arrows lean in roughly the same direction, toward a dusty, crowded slice of sky in Centaurus and Norma, where our own Milky Way blocks the view. That collective lean is what people nicknamed the Great Attractor, a gravitational pull with no single obvious culprit, and its value is not as a spooky object but as a lesson in how to read motion when the landscape is hidden. The clean, non-romantic story goes like this. Every galaxy participates in the overall expansion, but local clumps of mass clusters, filaments, even great walls tilt the flow. To see that tilt, you must subtract the expansion and keep only the peculiar velocity, which requires true distances rather than redshift alone. When you compile those distances across the nearby universe and compare them with the Hubble prediction, a coherent drift emerges in our neighborhood, a several hundred kilometer per second nudge that points near the zone of avoidance, where optical telescopes are least helpful, so you change the way you look. Radio maps at 21 centimeters trace neutral hydrogen through the Milky Way's dust. X-ray observatories see hot intracluster gas even when stars are obscured. Infrared surveys peel back the foreground glow, and together they reveal a crowded region of mass including the rich Norma cluster and the broader Hydra Centaurus structures that can plausibly account for a big share of the pull. But here's the part that matures, the myth. The Great Attractor is not a single hidden beast waiting to be unmasked, is a basin in the local velocity field, a low spot in the cosmic web toward which flows converge from many directions, and beyond it lies the even heavier Shapley concentration farther out, whose added gravity pulls on the same side of the sky and likely contributes to the overall drift. In that more honest picture, your local group first feels the Virgo cluster's tug, then weaves along filaments toward Hydra Centaurus, all while deeper mass in Shapley quietly biases the whole pattern. What once sounded like a mysterious, isolated force becomes a layered landscape of ordinary gravity spread over hundreds of millions of light years. The evidence for this is not a single smoking image, but a stack of cross-checks. The dipole pattern in the cosmic microwave background shows our bulk motion with respect to the universe's rest frame. Peculiar velocity catalogs reconstruct a three-dimensional flow that drains toward Centaurus. All sky, X-ray, and infrared counts find the very clusters. A flow-based map says should be there. And when you build cosmic flow-style models that integrate these data, you recover not a point attractor, but a watershed-hour supercluster basin. One elegant way to say it, coined by researchers who stitched these clues together, is to call our home region Laniakea, a catchment area defined by where the cosmic river runs downhill before the streams split toward other basins. In that atlas, the Great Attractor is the lowland at the center of our catchment, not a monster hiding in the reeds. Even the remaining uncertainty, how much is Hydrocentaurus versus how much is Shapley, teaches you how to do astronomy when you can't move your vantage point. You test your distance ladders until they agree within small, published errors. You design blind surveys in the zone of avoidance, so you don't only find what you expect. You watch for systematics and correct for them rather than wish them away. And you learn to combine many weak signals into a single, overdetermined map that leaves little room for wishful thinking. It's tempting to ask for a single answer. What is the great attractor, really? But the most accurate reply is a description of method and structure. It's the integrated pull of known mass at intermediate distance in the Hydrocentaurus Norma region, seen through our galaxy's veil, plus additional draw from deeper concentrations like Shapley, all acting on a web of galaxies whose filaments steer motions the way riverbanks steer water. There is no need for exotic new physics, only the patient mapping of mass you can and cannot see. For you, the takeaways are practical. First, the sky can hide huge things behind our own foreground, so no clear source is often a statement about observing geometry, not about the absence of matter. Second, motion is a truth-teller. Velocities, when paired with trusted distances, reveal mass that light alone can miss, turning the universe into a dynamical survey instrument. Third, the way the field grew past the headline by switching wavelengths, improving distance indicators, building flow reconstructions, and embracing the idea of basins instead of beasts, is a template for any problem where the obvious picture is blocked. Look sideways. Measure indirectly and expect the answer to be distributed rather than dramatic. So let the hook be the tug you can feel but not see. Let the development be a calm tour through peculiar velocities, zone of avoidance tactics, clusters that glow in X-rays, and basin over traction maps that stitch it all together. And let the conclusion land softly. The great attractor is not a single secret hidden in the dark. It's a subtle valley in the fabric of our local cosmos, and learning to read its pull turns a rumor into a river map of where we live. Galaxy superclusters, Titanic cities of galaxies. Picture a city whose blocks are not buildings, but galaxy clusters, whose avenues are rivers of galaxies, and whose suburbs are gauzy filaments of faint gas that stretch that city across hundreds of millions of light years, and you have a galaxy supercluster, the largest recognizable neighborhoods of structure the universe knits for itself. You live in one of these vast districts, and learning how they form, how we map them, and how they reshape their residents gives you a workable compass for the cosmic web, rather than a postcard of pretty dots. Start with the definition that refuses to be tidy. A supercluster is not a single, relaxed object like a galaxy cluster. It's a loose association of clusters, groups, and filaments that share a common overdensity and flow pattern. A region where gravity has carved a basin so that galaxies tend to drift the same way even if the whole district is not and may never be fully bound. Because city limits are fuzzy, astronomers draw them with methods that are honest about what's measurable. In redshift surveys that map millions of galaxies, a friends of friends algorithm links objects that are unusually close in three-dimensional space, revealing chains of clusters and groups. Other catalogs define superclusters by tracing density ridgelines through the distribution, or by reconstructing the local velocity field and marking the watersheds where flows converge, like labeling entire river basins instead of just towns along the water. No matter which door you use, the picture that emerges is consistent. Superclusters are knots and corridors in a foam-like cosmic web, with clusters as the bright downtowns, filaments as the highways feeding them, and vast low-density voids as the dark countryside between. What makes them trustworthy is not the romance of the map, but the cross-checks beneath it. Optical redshifts reveal where galaxies share space. X-ray images show the hot, intracluster plasma that only deep gravity wells can hold. Radio and microwave observations catch the Sunyav-Zeldovich imprint, where fast electrons in cluster gas nudge background photons, and gravitational Lensington, coherent distortions in the shapes of many background galaxies, draws a mass map that includes dark matter as well as light. When these agree, you aren't squinting at you are tracing real architecture. On sizes of a few 100 million light-years, another ruler appears, the Baryon acoustic feature, a preferred separation left by early universe sound waves, shows up as a faint excess of galaxy pairs at a characteristic scale. That yardstick does double duty, anchoring the map's distance, calibration, and reminding you that superclusters are not arbitrary agglomerations, but grow from ripples seeded in the first thousandth of the universe's life. Dynamics keep the story honest. Within a cluster, the dense city-core galaxies move so fast, and the potential well is so deep that the system is bound and often relaxed. Between clusters, along the filaments of a supercluster, the situation is more like a metro region still under construction. Material streams inward along multiple avenues. Small groups merge into bigger ones, and shocks ripple through the thin, warm, hot intergalactic medium that threads the roads. Because the universe's expansion is now accelerating, many superclusters will never collapse wholesale into single compact objects. Parts will remain loosely connected, and only their densest kernels will stay bound far into the future. That matters for language. Calling a supercluster a structure is fair. Calling it a single object is not. If you want to see their motion with your own mind's eye, look at the fingerprints that velocity leaves on surveys. Redshift space distorts true positions in ways that are diagnostic. Inside clusters, random high speeds smear galaxies into fingers of God pointing along our line of sight. On larger scales, coherent inflow toward mass concentrations squashes the pattern in characteristic ways. By modeling both effects, you can weigh the underlying gravity field without ever touching it. Push further, and you can reconstruct the three-dimensional flow itself from distance indicators using supernova, surface brightness fluctuations in old stellar populations, or the tight scaling relations that link a galaxy's rotation or velocity dispersion to its luminosity. And those flows drain into supercluster basins the way rain organizes into watersheds, confirming that what looked like a city on a static map is also a living drainage of matter. Life inside these titanic cities is not neutral. It changes galaxies. A small group slide down filaments into cluster downtowns. They are pre-processed. Their star formation begins to wane. Their gas halos are nibbled away in encounters. And then, upon entering the hot cluster medium, ram pressure stripping and repeated high-speed flybys finish the job. Turning blue, gas-rich spirals into red, gas-poor residents that age quietly. You can watch this transformation happening. Jellyfish galaxies trail luminous gas tails as they're degassed. Cluster collisions inside a supercluster light up the radio sky with giant arc-shaped relics where merger shocks re-energize particles. Diffuse radio halos bubble up in cores where turbulence stirs magnetic fields. And faint, thread-like bridges of X-ire and ultraviolet emission trace filaments where gas is finally being found in the missing baryon phase to cool for X-ray brightness. Too hot and thin for easy detection, yet visible where it's compressed by the cosmic freeway's gentle traffic. Beyond the eye candy, superclusters give you leverage on fundamental parameters. Count clusters above a given mass across a large volume, and you get a sensitive test of how fast structure grows, which depends on both the cosmic matter budget and the rules gravity follows. Map how galaxies align, their spins with nearby filaments, and you learn how tidal torques from the web sculpt angular momentum. Measure how the lensing signal and the galaxy distribution relate, and you calibrate how faithfully light traces mass, a necessity when you want to use galaxies as stand-ins for the invisible scaffold beneath. Even their sheer extent is instructive. Long walls that look too enormous to be comfortable can usually be explained as chance, alignments of several adjacent superclusters and filaments rather than single. Monolithic slabs reminding you to respect statistics before declaring a cosmic violation. The practical craft behind all this is worth copying outside astronomy. When the Milky Way's dust hides a swath of sky, observers switch wavelengths to infrared and radio. When redshift space lies, model the lie and invert it. When one tracer is biased, combine many. When definitions are fuzzy, prefer ones tied to measurable flows rather than arbitrary cutoffs. It's the same posture you need any time a system is bigger than your field of view. Build multiple, imperfect maps and let their overlaps tell the truth. Neither could alone. What should you keep from this tour that actually upgrades your intuition? First, a supercluster is a district in a living web, not a sculpture. Its edges are where flows diverge, not where bricks end. Second, galaxies are citizens whose fates are written partly by address filaments feed. Groups pre-process, cluster cores, quenchand. Those environmental verbs show up in real images and spectra, not just in cartoons. Third, the very act of mapping these cities by hot gas, microwave imprints, and precise distance ladder turns grandeur into measurement. From how fast clusters merge to how thin gas glows along a bridge, each small, careful number teaches you how the largest things grow. So let the hook be a city so large its avenues are galaxies. Let the development be a disciplined reading, definitions grounded in flows, maps stitched from light and gravity, dynamics that separate bound cores from loose burrows, ecology that transforms residents along the commute. And let the conclusion rest in a calm thought. You don't have to memorize the whole web to navigate it. You only need to learn what a basin looks like, where the highways run, and how to trust instruments over instinct. Because in a universe that builds titanic cities of galaxies, clarity arrives the same way it does in any human city, by seeing how the streets connect and noticing which way the traffic goes. Cosmic voids, enormous regions with almost nothing inside, begin not with a crowded skyline but with quiet. Imagine panning your view across the universe and lingering not on the glittering avenues of galaxies, but on the vast dark in between. Regions so underpopulated that for tens to hundreds of millions of light years, you could drift without meeting a single bright city. These are cosmic voids, and their lesson is counterintuitive, but powerful, that emptiness has structure, that almost nothing evolves, and that the best tests of gravity and growth sometimes live where there is the least to see. A working picture starts simply, in the young universe. Some patches began a little denser than average, and others a little thinner. Dense patches slowed their expansion and gathered matter into filaments and clusters, while thin patches did the opposite they expanded a bit faster than the average, evacuating material toward their edges. Over billions of years, that gentle bias turns into geography. Voids become underdensities that can be 80 to 90% below the mean, surrounded by walls and filaments that receive the outflow. They aren't empty bubbles with crisp borders, and they aren't spheres. They are lumpy rooms in a foam, stitched together by boundaries where flows diverge. Their growth has a hierarchy. Small voids inside larger underdensities merge into roomier chambers, void in void, while small voids embedded inside. Big overdensities can be squeezed out of existence as the surrounding mass collapses because the center of a mature void keeps expanding a little faster than the cosmic average. Galaxies inside it experience a coherent push, outward peculiar velocities that point from the middle to the walls, leaving a kinematic fingerprint we can read in surveys as an elongation of stacked voids along the line of sight. That is one way we know voids are not just cartographic artifacts. Their dynamics agree with their maps. Mapping them well demands a different mindset than hunting clusters. You don't merely plot bright dots. You trace the shape of absence with many imperfect traces. Galaxy redshift catalogs reveal where the density falls off. Watershed algorithms follow the ridges between basins to define void boundaries in 3 dimensions. Cross-checks with weak gravitational lensing confirm that light passing through voids is very slightly demagnified in background. Galaxy shapes are coherently distorted in the opposite sense of a mass concentration, a subtle anti-lensing that only emerges when you stack many voids. Gas physics adds its own thread. Most of the missing baryons hide in the thin, warm hot filaments that lace between walls. But inside the deepest voids, the intergalactic medium is even more rarefied and cooler. You meet it indirectly as a paucity of Lyman alpha absorption lines along quasar sightlines, and in the future as a gentle dip in 21 centimeter intensity maps when neutral hydrogen surveys mature. Because void galaxies evolve with fewer collisions and less harassment than their cousins in busy districts. They are a natural experiment in ecology. On average, they are bluer, more gas-rich, lower in heavy elements, and still forming stars at modest rates. Their disks can be more extended and pristine, their bars rarer, their outer gas less stripped. Even the dark matter halos they inhabit tend to be lower mass and less concentrated, telling you that environment is not flavor text, but a force. Address shapes, biography. The quieter conditions make voids exquisite laboratories for fundamental physics precisely because many messy effects are weaker there. In low-density regions, several screening mechanisms that hide modifications of gravity in crowded places turn off or relax. So alternative theories predict different outflow speeds, different density profiles at void edges, or different lensing signals than standard gravity does. Measuring the redshift space distortions of galaxy flows around stacked voids, and comparing them to the very weak lensing maps, gives you a clean growth of structure test that is hard to fake with baryonic complexities. Voids also feel the whisper of massive neutrinos, because neutrinos free stream and refuse to clump on small scales. They effectively fill in voids a bit, making them less empty and their edges less sharp. That gentle smoothing leaves signatures in the statistics of void sizes and profiles that future surveys can turn into an independent neutrino mass constraint. Even dark energy can be probed with emptiness. If you take many voids at similar distances and stack them, their average shape should be statistically round. Any squashing or stretching you see after you correct for outflows is a purely geometric Alcock-Pachinski signal that ties together the expansion rate and distance scale at that epoch, because the method is based on geometry rather than brightness. It dodges some of the calibration pitfalls that afflict traditional candles and rulers. Meanwhile, lines of sight through supervoids ever so slightly cool the cosmic background photons that cross them, adding a tiny temperature decrement you can pick up only in stacks. Whether that late-time imprint is exactly as strong as simple models expect is itself a teachable tension, spurring better maps of both matter and microwave sky without needing a sweeping new ingredient. If you're picturing only featureless hollows, add more texture to your imagination. Voids are not dead. They host dwarf galaxies discovering slow adulthood, faint tendrils of gas stretching between small groups, and occasional tunnels where two voids have merged and left a thinner wall. Their boundaries are not hard shells, but crowded compromise zones where infall along one filament meets infall along another, birthing shocks that warm gas and seed magnetic fields. Radio telescopes find giant, diffuse relics and halos in clusters at these junctions, the broader supercluster scaffolding made visible by particles freshly stirred. From a mapmaker's perspective, void statistics, how many there are of a given size, how they cluster, how round they are, carry nearly orthogonal information to the usual galaxy two-point functions, which is a wanky way of saying that adding voids to your cosmology toolkit raises the total information content because you are asking the data a different question. From a craft perspective, every challenge has a measured answer. The Milky Way's dust obscures parts of the sky, so move to infrared and radio to keep the catalog uniform. Conversions from redshift to distance distort true positions, so model those distortions and invert them instead of pretending they aren't there. Galaxy tracers can be biased relative to mass, so anchor your void catalog with lensing and with multiple galaxy samples of different brightness to track that bias. Definitions are fuzzy, so prefer flow-based boundaries watersheds in the reconstructed velocity field when you can, and be explicit when you use density-only criteria. Do this patiently, and voids stop being a curiosity and become rulers, clocks, and laboratories all at once. The philosophical payoff is practical. The universe's largest lesson in humility is that absence can be as informative as presence. By reading the way nothingness expands, you weigh the rules that govern everything. For you, the hook is that a map of where galaxies aren't turns out to be a sharper test of cosmology than yet another picture of where they are. The development is the concrete craft hierarchical growth that evacuates centers. Redshift space elongation from coherent outflows. Anti-lensing that confirms mass deficits. Blue and gas-rich residents living slow lives. Geometric tests that do not rely on candles. And sensitivity to neutrino fog and to any tweak in gravity's reach. And the conclusion is a soft, durable thought. When you train yourself to learn from the quietest places, you carry home more than a new fact about the cosmos. You carry a method, one that prefers clean signals over drama and that can be reused anywhere your world seems too busy to understand. By stepping first into the calm. The Sloan Great Wall, a gigantic structure of galaxies. Trace a line on the universe's map and find not a neat border, but a ragged continent of structure. The Sloan Great Wall entered astronomy as the moment a three-dimensional survey stopped being dots on paper and became urban, planning at cosmic scalar, sprawling chain of galaxy clusters. Groups and filaments stretching for well over 1 billion light, impressive enough to feel rule-breaking yet, when read with the right tools, perfectly compatible with how structure is meant to grow. Start with what wall really means here, because the word tempts the mind into picturing a monolithic slab. In large-scale structure, a wall is the statistical crest of an overdense sheet in the cosmic web, a stitched-together corridor where filaments meet and clusters crowd, with underdense voids on either side, more quilt than concrete. The Sloan Digital Sky Survey earned its headline by giving us millions of galaxy redshifts in a contiguous swath of sky. Convert those redshifts to distances carefully separating the part due to expansion from small local motions. Plot the points in true three-dimensional space, and a pattern appears. Chains of superclusters linked by fragments into an extended ridge, no single object in the everyday sense, but a continuous, navigable overdensity whose coherence is physical, not a trick of perspective. You know it is physical because independent tracers agree. Clusters embedded in the ridge shine in X-rays from hot gas trapped by deep gravity wells. The background microwave glow is nudged along those same wells by electrons in that gas, a subtle Sunyav-Seldovich signature. Weak gravitational lensing sketches a massed contour that includes dark matter as well as stars, and galaxy velocities on the wall's flanks show the expected pattern flows, tipping toward the sheet and then sliding along it toward brighter knots. When you model the distinctive distortions, that peculiar motion imprints on redshift space. Yet the lesson of the Sloan Great Wall is not giant things overturn our assumptions. Its giant things require precise language. Cosmology expects a cosmic web with walls, filaments, and nodes grown from tiny early ripples. It also expects that, when you average on large enough scales, the universe looks statistically uniform, a concept sometimes called the end of greatness. The wall tests both halves of that expectation at once. Yes, a single, named structure can be eye-wateringly long, because walls percolate and merge. And yes, this does not violate uniformity, because uniformity is about averages over many such features, not about forbidding any one crest from being grand. In practice, whether a feature deserves a name depends on how you draw boundaries, and here method matters. Link galaxies with a friends of friends algorithm using a chosen linking length, and you will watch separate clusters coalesce into superclusters and then into grander ridges. Lengthen the link too much and everything percolates into one monster. Shorten it and you fracture a city into neighborhoods. To keep ourselves honest, we measure the wall's reality with statistics that ignore names. Minkowski, functionals, and genus. Curves quantify how sponge-like the map is. Minimal spanning tree and skeleton analyzes trace the web's backbone and count branches. Percolation thresholds tell you when local overdensities join into a spanning network. Mock catalogs, drawn from simulated universes, put error bars on how often a ridge as long as this should appear. Those blind tests consistently say the same thing. The wall is a high but not impossible crest in a CDM universe, a product of ordinary gravity acting for a long time on slightly lopsided initial conditions. If all you remember is a headline like bigger than expected, you miss the discipline underneath. The headline came only after comparing to mocks with the survey's actual footprint. Selection function and sky mask baked in because survey geometry can manufacture features if you are careless. The same caution applies to distance. Redshift converts to comoving distance only after you model how local velocities stretch or squish patterns. Within clusters, random speeds make fingers of God that point along our line of sight. On larger scales, coherent infall toward massive ridges, compresses contours. Interpret both correctly, and the wall's thickness and length stabilize, freeing you to ask ecological questions instead of arguing about shadows. Ecology is where a named structure earns its keep. Along a wall, the inflow is anisotropic. Galaxies and groups stream in along a small number of preferred highways, which changes how they live before they ever hit cluster cores. You can watch pre-processing in action, star formation, slowing in small groups on the approaches, gas reservoirs thinning before the final plunge, jellyfish galaxies showing one-sided gas tails where the thin, warm intergalactic medium of the corridor already nibbles at them, radio relics lighting up at shocks where filaments collide, and faint bridges of X-ray and ultraviolet emission revealing the elusive, warm hot medium that ties the ridge together. Because the wall is extended, it also becomes a calibration tool. Count clusters above a given mass, along and around it, and you probe how fast structure grows. Compare lensing maps with galaxy counts, and you refine how faithfully light traces mass, the bias. Measure alignments of galaxy spins and shapes with the local web, and you test tidal torque theories of how galaxies acquired their angular momentum. Lay the Baryon acoustic standard ruler across the same volume, and you confirm that this spectacular wall is built on ripples set in the first thousands of cosmic seconds, not on some separate, late-time process. There's even a pedagogical gift in the debates the wall sparked. Claims about largest ever taught the field to be explicit about definitions as the structure contiguous under density thresholds, or topologically connected under watershed flows. To quote uncertainties that include the Luckel's-Ware penalty for surveying vast volumes, and to avoid comparing apples to oranges by mixing walls mapped in galaxies with walls inferred from unrelated traces like gamma-ray bursts. By that standard, the Sloan Great Wall sits exactly where it should, remarkable, instructive, and a little messy, like any real city. The practical posture you can take away works outside cosmology. 2. When a feature seems too big to be ordinary, change your question from "is this allowed?" to "what statistic does it maximize? How often should that maximum occur in my measurement volume? And what independent tracers can confirm it without sharing my biases?" If you do that here, the narrative calms and deepens. The wall is a stitched crest in a foam of matter, visible because a modern survey finally had the reach and uniformity to show it. It neither breaks the cosmological principle nor reduces to a naming trick. It becomes a laboratory for how galaxies grow along supply lines and a benchmark for simulations that must produce not just the right averages, but the right rare features. Let the hook be a ridge so long it outruns your intuition. Let the development be the method how surveys turn redshift into geography, how topology and percolation replace romance with measurement, how multi-wavelength tracers and velocities make a mass-bearing map, how ecology along the ridge teaches you the verbs of galaxy evolution, and let the conclusions settle softly. The Sloan Great Wall is not a wall that stops anything. It is a mapmaker's gift that connects reasons why the web looks the way it does, why averages can stay simple while details get grand, and why the right statistics let a billion light-year headline become a precise, testable story about how a universe builds cities. Baryon Asymmetry. Why matter won over antimatter? Begin with a quiet, unsettling question you can feel in your hands. If the early universe made matter and antimatter in almost equal amounts, why is your hand this table, the air, the earth made of matter at all instead of nothing after a perfect, mutual annihilation? The honest answer is that somewhere in those first moments, the balance tipped by the tiniest margin, roughly one extra matter particle for every billion matter-antimatter twins, and when the pairs destroyed each other, that 1 in a billion excess survived and eventually became everything you know. So the puzzle called Baryon asymmetry is not trivia, but the reason there is anything left to think with, to turn that into a teachable path. Imagine the rules you'd need if you were designing a universe and wanted a small bias to emerge from symmetric beginnings. 3 ingredients are unavoidable. First, you need reactions that can actually change the how many baryons bookkeeping. Otherwise, nothing you do can move the needle. Second, you need the laws to treat matter and antimatter slightly differently, an asymmetry in their behavior, so that averaged over many events, one wins by a hair. Physicists call that kind of difference a violation of certain symmetries that swap particles with antiparticles and mirror their motions. Third, you need a moment when the cosmic chemistry falls out of perfect balance, so the tiny preference doesn't get washed away like taking a pan off the heat at just the second, when one side of the souffle has risen a whisper higher. Those 3 requirements sound abstract until you connect them to real evidence and concrete mechanisms. Evidence first, the ratio of leftover baryons to background light is encoded in 2 independent cosmic ledgers, the light chemical elements forged in the first minutes and the faint ripples of the microwave background much later, and both tell the same story, pointing to that 1 extra per billion excess with remarkable precision. Meanwhile, sky-wide searches haven't found the fingerprints we would expect if there were entire antimatter neighborhoods, no convincing antihelium among the rain of high-energy particles, no persistent glow from annihilation where matter and hypothetical antimatter domains might rub, no cluster that betrays itself as a mirror twin by the way it seeds telltale gamma rays. So the simplest reading is that the whole accessible cosmos shares the same sign we do. Mechanisms next, and here is where you trade romance for craft. The known menu of particle physics already contains a sliver of the second ingredient, a difference between matter and antimatter. Certain unstable particles made of quarks decay a touch differently than their antiparticles, an effect discovered decades ago and measured with exquisite care in laboratories that watch billions of decays. Beautiful as it is, that built-in bias is far too feeble. And another bottleneck appears, the change of bookkeeping reactions. The known forces provide at the energies the young universe actually had, and not the right kind to lock in a big enough imbalance. In the textbook standard model, the cosmic transition when the electroweak force split into the separate electromagnetic and weak forces was not a violent, bubbly event but a smooth crossover. So the out of balance at the right moment requirement is also not naturally met. That leaves you with 2 broad families of ideas that are conservative, not in style, but in method. Tweak the physics near that transition, so it becomes a frothing first-order change with new particles and new sources of matter-antimatter difference, electroweak, barogenesis, or make the bias first in the lepton sector. The family that includes neutrinos and, let known high-energy rearrangements, convert part of that lepton imbalance into a baryon 1 leptogenesis. The first path, electroweak, reads like a controlled experiment you could someday diagnose with multiple instruments. If the cosmic transition involved expanding bubbles of a new phase, sweeping the universe, then particles reflecting from and transmitting through those bubble walls could experience tiny asymmetries that pile up a net excess on one side. To make this work, you need extra sources of antimatter difference beyond the ones already measured in quark decays, and crucially, you need the transition to be sharp enough that the universe really was briefly out of equilibrium. Models that add new Higgs-like particles or extensions of the known fields can supply both tweaks, and they make testable predictions. New heavy particles at colliders, small electric dipole moments for the neutron or the electron that are just within reach of evermore, sensitive laboratory experiments, and even a faint background of gravitational waves from the violent shaking of those bubbles a hiss in spacetime that future space-based detectors could hear. The second path, leptogenesis, starts from a different clue hiding in plain sight. Neutrinos have mass, which the basic standard model cannot explain without adding new ingredients. One elegant fix introduces heavy, right-handed partners that would have existed in the early universe, decayed slightly differently into matter and antimatter, and done so while the expansion kept the reactions from fully averaging out. Known electroweak processes then shuffle a fraction of that imbalance from the lepton side into the baryon side. This picture is attractive because it crams two birds into one sensible bag: neutrino masses and matter's triumphant it. 2. Makes predictions you can hunt, a measurable difference between neutrinos and antineutrinos. In oscillation experiments on Earth, rare patterns in the way the lightest neutrinos mix, or if the heavy partners ever had lighter cousins, indirect traces in precision. Measurements at colliders and intense beam facilities. If grand unification tempts you a framework in which the forces we know merge at ultra-high energies, there is a third family where massive, short-lived bosons that existed only in the earliest instance favored decays that added more quarks than antiquarks. Those same ideas usually imply that ordinary protons should very rarely decay, so giant underground detectors keep watch for telltale flashes in tanks of pure water or liquid snow. The long, patient absence of such decays does not kill the idea, but it fences it with numbers and pushes models toward corners that are hard but not yet closed. There are even more exotic proposals: fields that rolled and pooled a bias as the universe cooled, phase transitions that temporarily gave space a directional grain and then erased it, but the mature plan is always the same. Tie any bold story to more than one thread of data so that future measurements can falsify it cleanly rather than argue about taste. That is why the most interesting searches for why you exist are scattered across very different laboratories. High-precision studies of rare decays and subtle electric dipole moments limit or reveal new sources of matter-antimatter difference. Neutrino experiments stretching for hundreds of kilometers look for a phase in the mixing of flavors that would tip neutrinos and antineutrinos into different rhythms. Collider teams hunt hints of new scalar particles that would have made the early universe transition violent enough. Cosmic microwave background and galaxy surveys pin down the exact amount of leftover matter your theory must produce, leaving little room for fudge. And gravitational wave observatories prepare to listen for the murmur of any early universe boiling that a successful electroweak scenario would have left behind. Through all of this, you keep two guardrails up. First, do not mistake ignorance for license. Nothing in current observations forces you to abandon known physics. But known physics as it stands is insufficient. So the job is to add the least while explaining the most. Second, do not romanticize mystery. "We don't know yet" is not a shrug, but a disciplined program with concrete milestones and multiple ways to be wrong quickly. What should you carry out of this beyond awe? A few robust truths. The universe keeps a precise account. The matter excess is tiny but measured, and it aligns across independent cosmic inventories. Antimatter is not demonized or banished. It is simply rare on large scales today, and we would have seen the scars if equal domains still shared our sky. The ingredients any successful explanation must bake in reactions that change baryon count, a genuine matter-antimatter difference in the laws, and a period out of balancer, specific enough that entire fields of experiment have grown up to test them, and the method that makes sense of the problem, refusing to let one type of measurement carry the whole claim, insisting that collider data, tabletop precision, neutrino beams, sky maps, and gravitational wave listening all rhyme turns a poetic origin question into practical, solvable science. Let the hook be the fact that everything you love is a 1 in a billion remainder. Let the development be the calm architectural what the cosmos measured, why 3 conditions are necessary, how electroweak bubbles, heavy neutrino decays, or grand unified relics could have delivered the bias, and where the next honest clues will come from. And let the conclusion land softly. You do not need to invent fables to feel wonder, because the real drama is this: our existence is the faintest asymmetry written into the first minutes, and learning exactly how that script was authored is a patient collaboration between the smallest experiments on Earth and the largest experiments the universe ran once and keeps letting us read.